Salutations à tous, greetings everyone. Bienvenue à ce premier congrès international de la jeunesse astronomique. It is with a great pleasure that I welcome you to the first edition of the International Congress of the Astronomical Youth. My name is Alexandre Bellon, and I'm the Vice President of the Youth Commission from the French Astronomical Society, in charge of projects. I will be accompanying you throughout this Congress and welcoming our various speakers. We have prepared an exciting program for you with inspiring presentation and stimulating discussions on the latest advance that is the James Webb Space Telescope. I wish you all an excellent Congress that is now officially starting. First of all, we would like to express our sincere gratitude to our partners, National Center of Space Studies, French Atomic Energy Commission, Astronomisk Ungdom, IPSA VEGA, and Haikintana for their invaluable support to the French Astronomical Society in making this Congress a reality. The objective of this Congress is to bring together the astronomical youth on an international level into a strong and unified community. At a time when sciences and astronomy are increasingly undervalued, with this event, we hope to foster collaboration, knowledge sharing, and amateur development among the next generation, our generation. Furthermore, the staff will be delighted to answer any question you may have in the chat room at any time during this Congress. We'll find an important source of information in the description. The program is included. For the first edition of this Congress, we have a fantastic lineup of speakers. We are honored to welcome Dr. Elbaz, Scientific Director of the Astrophysics Department at ICAY, who will share his insights on the latest development in this exciting field. We'll also have Dr. Lagage, Co-Director of MIRIM Instruments, who will discuss the instrument contribution to infrared astronomy. In addition, we'll hear from PhD student Marion Zannese, who is working on JWST results and will offer a glimpse into this cutting-edge research. In addition to those esteemed speakers, we'll also be hosting Astronomisk Ungdom from Sweden and the association behind Madagascar's first observatory, Haikintana. They will provide unique perspective on astronomy, education, and outreach in their respective regions. Finally, we're excited to announce that Haikintana will be joining us at the end of this Congress. They will be streaming an observation from the observatory in Beseli, Majunga, which is situated in the southern hemisphere and boasts some of the clearest skies for astronomical observations. Allow me to introduce Liv Sivé. The young president of the Youth Commission will be presenting the French Astronomical Society and this commission. Liv, good afternoon and welcome.
Hello.
You are a passionate young astronomer. So the Youth Commission is a novelty, the French Astronomical Society, who have been founded in 1887, isn't it?
Yeah, exactly. So let me just share my screen. Yeah. So does it work?
Yes.
Yeah, perfect. So actually that's exactly correct. So, well, what's the SAF? It's the French Astronomical Society. You can also see the SAF logo just here. And in French, we call it La Société Astronomique de France. So, as Alexander said, the SAF was created in 1887. It is therefore a rather old society and rich in history. But I will not tell you more here. Let's just say that it was founded by the French scientist Camille Flammarion, that you can see just here. And it is now chaired by Sylvain Boulet here, the planetary scientist, university professor, and passionate about the planets Mars and asteroids. It is thanks to his trust that this Congress is possible, so thank you, Sylvain. And the main objective of the SAF are nowadays to bring together professional and amateur together. So, to reach this objective, the SAF is organized around 4 main axes that you can see just here on this screen. So first of all, to observe and to discover with its observatories like Juvisy, Triel, Belasta, La Sorbonne, which often welcomes the public. And even in Madagascar now, we're going to talk about it again tonight. And secondly, read and understand. So L'Astronomie is a reference scientific monthly magazine made by the staff. There are also publications, books, ephemerides. So the staff is really active in publication and the transmission of information in very related events because many professionals participate. So then we have Meet and Learn with events like AstroCiel, an annual meeting to exchange between passionate people, share and practice together on their beautiful sky. There are also training cycles and monthly conferences and the co-organization of the staff also for the Florence Festival in France. And finally, in my opinion, this is the reason of the current dynamism of the staff. We have, so here are the photos for Meet and Learn. So we have share and collaborate with the staff. So there is 15 different commissions. These commissions make possible to group passionate people around a specific astronomical field. So each commission has management office with a president, vice president, and secretary. And they organize activities for members. You understood that's great because amateur can be in contact with professionals and work together on projects. And I will show you, I will not name them all, but to show you the diversity of that we have here, we have the double star commissions, the planetology one, instruments, history, and YANT, of course. So this is the perfect transition to tell you about the YANT Commission, very recently opened within the staff, and which is therefore at the origin of this Congress. So we have three different main goals. So the first one is to bring together young people aged 11 to 25 around their common passion for astronomy. Then the second point is to share project internships, schools, career paths, so all the things related to professional career. And then the third one is to allow young people to meet astronomers and astrophysics. But we have a problem here. We have a geographical problem. Astro teams are spread over French territory, so we created, this is our solution, we created a Discord server. So, for those who don't know about it, it's a digital platform with flexibility to create new spaces at the request of the teams on the server. So we have voice room with this little logo. We have text rooms here and voice rooms here, sorry. And it allows us to host professionals on our server every month for speech. And this server is also called Universe, by the way, in the reference of the competition that gave birth to this commission. And so even if it's not great as the physical meetings, it contributes to the exchange of young people around their common passion. And so I think it's a good way to share. So there you go. I hope you know our beautiful organization better now. So good congress to all, and thank you for attention.
Thank you, Liv. Dear attendees, the question you may have will be answered in the chat room, so do not hesitate. Let's start the conferences series. I'm really pleased to welcome Dr. Lagage, co-director of MIRIM Camera, currently at the James Webb Space Telescope. Launched in December 2021, the JWST is the largest and most complex telescope ever built, boasting outstanding performances that exceeded its specifications. With its vast collecting surface and large wavelength coverage, the telescope will have a significant impact on many astrophysical fields, enabling us to observe further and probe the universe at the time of the first galaxies. We will relay your question live to Dr. Lagage, so please do not hesitate to ask them in the chat room. Sir, thank you for coming. The floor is yours. I think you don't have your mic on.
Can you hear me?
Yes.
Good. So thank you very much for the invitation. It's a pleasure to be with you and to present the James Webb Space Telescope. So first, let's give you some important background. So as you know, the messenger to know what is happening in the universe is the light. And some basis before starting is that, as you know, the light has a finite speed. So when you are looking further away, you are looking in the past. So to give you some example, the light coming from the moon has 1 second from the moon to the Earth, 8 minutes from the sun to the Earth, 4.2 years from the nearby star to the Earth, 26,000 of years from the center of our galaxy to the Earth, and 2.3 million years from the nearby galaxy to us. And the latest information, the further away information we have is a cosmic background, which is 13.8 billion of years. So with Hubble, we were able to look further and further. So as a function of time, you can see that Hubble is able to see objects which were about 4 million years old compared to the Big Bang. But Hubble has reached its limits. Why? Because it is in the visible or near infrared. And you have the reddening of the light with the expansion of the universe. So Hubble could not go beyond what he has reached so far. And it is a pity, because just beyond the limit of HST, there are very interesting stuff, what we call end of dark age. So here you have a thematic view of the evolution of the universe from the Big Bang, from the recombination of electrons and protons, which gave this cosmic background. And then it was dark, no light. And we have to wait for the first star, first galaxy to be formed. This is called the dark age. And Hubble was not able to access to this end of dark ages. And this is something completely unobserved so far. And it is, of course, very important to know when the first star, the first galaxy formed. So to do so, we need a larger telescope and a telescope detecting the infrared light. And this telescope is the James Webb Space Telescope, with a collecting area of 25 square meters. So you are young people. I'm not sure your flat is as big as a mirror of James Webb. Often my student, my PhD student, has a flat of 20 square meters. So you can see that how big is this telescope. And the wavelength range go from 0.6 to 28 microns. So from the near to visible, near infrared, and mid infrared. This is a flagship mission from NASA with participation of the European Space Agency and the Canadian Space Agency. What ESA, the European Space Agency, is doing, ESA provided the launcher, an Ariane 5, and provided also a full instrument, the near infrared spectrometer, NIRSPEC, as well as part of the MIRI instrument. And the MIRI instrument was done by a consortium of laboratories in Europe and in US. In addition, Europe is providing 15 ESA staff members at the Science Operations Center, which is at Baltimore in the US, It is the same center as the Hubble Space Telescope Center. So often it is said that the Webb telescope is a successor of the Hubble Space Telescope. But it is also the successor of the Spitzer telescope. The Spitzer telescope was the previous infrared telescope. And the improvement in terms of sensitivity from Spitzer to James Webb is enormous. The size of the Spitzer telescope was only 85 centimeters, to be compared with the 6.5 meter of the primary mirror of the Webb telescope. HST was already a 2.4 meter telescope. So the difference between HST and James Webb is, of course, the increase in the size of the mirror, but above all is the wavelength coverage. So, but compared to Spitzer, the increase in size is enormous. So it has been a very challenging telescope. It was the first time that we had an infrared telescope deployed in space. So let's see first the launch. So the launch was perfect. It happened on the Christmas day in 2021. I had the chance to be at Kourou at the CNES base to see the launch. And why did I say that the launch was perfect? You have some characteristics, some requirements in terms of what should be the trajectory of the launcher. And you have, of course, a nominal trajectory and some possible deviation, which are completely acceptable. And in fact, the launch was so close, very close to the nominal requirement, very, very close. Why do I say so? I say so because there were some propellant which was reserved to adjust the trajectory. And it was not used, which means that we have propellant for 26.5 years. That means that from this point of view, the James Webb could be in operation much more than the 10 years of the requirement. And maybe you surely know that Hubble has been in operation since more than 30 years. So if we could have James Webb in operation for 26 years, that would be fantastic. And the first thing was that Ariane make it possible. Of course, there are other factors which could limit the lifetime of James Webb. But at least we have very good news in terms of propellant. So the second thing which was very challenging was the deployment. You can see on the left, the telescope as it was completely packed to enter in the rocket. And you can see it after deployment. So there have been several deployments. So one critical was the screen, the thermal screen, which prevent the sun and even the Earth radiation to hit the telescope. As it is an infrared telescope, the telescope should be cool in order that its own emission doesn't perturb the observation. And for that, it is passively cool, so naturally it cools, but if it would have been hit by a photon from the sun or the Earth, it could have a higher temperature. So this thermal shield was crucial to get the right temperature, low temperature of the telescope. And you can see that it is a huge thermal shield about the size of a tennis court. So that was really challenging. And everything worked perfectly. And the temperature of the telescope is the one we wanted to achieve, which is minus 223 degrees Celsius. The mirror instrument had to be cooled at a lower temperature because it is in the mid-infrared. So the temperature has to be at 7K, and for that, we need a machine. So it was not cool passively, but cool with a special machine. 1 month after launch, it has been the insertion of the telescope around the L2 point. The L2 point at 1.5 million kilometers from the Earth is a special point where the gravity from the sun decreases, of course, compared to the gravity at the Earth, but the Earth also has some gravity impact, and the combination of the sun and the Earth's gravity make the speed, the angular speed of this point, the same as the Earth's angular speed, which means that Sun, Earth, and this point are always aligned. And it was really important for the thermal shield not to be very, very big. Then another challenges was the phasing of the hexagonal mirror of the primary mirror. You know, the primary mirror is made of 18 segments, and behind each of these segments, there are 7 actuators which allow to give the final shape of the mirror. That's a crucial difference with Hubble. Hubble, it was a mirror, one-piece mirror, which should have its final form on Earth. For that, it has to be thick and so on. Here, as the final shape is given during flight, you can have a much thinner mirrors, and the weight of the James Webb mirror, the 6.5 primary mirror, the weight is lower than the weight of the 2.4 meter mirror of HST. And it is because of this completely new technology for space, the fact that to give the shape of the final shape of the mirror with actuators during the deployment. So on the left, you have the 18 images before the adjustment of the shape of each hexagon. So the shape was made okay, and after that, it was been the time of instrument commissioning. There are 4 instruments on James Webb. So you can see that the coverage, the wavelength coverage, start from 0.6, which is the visible, up to 28 microns. 3 instruments, NIRSPEC, NIRCam, and NIRIS, cover the 0.65 micron range. With such instrument, you can do, of course, imaging, classical imaging with various filters, infrared filters. You can do also coronagraphy observations. That means to hide the star and see what is around it. And of course, you have very important spectroscopic possibilities, either with a single slit or, which was the first time in space, multi-object spectroscopy. In the 5 to 28 micron range, you have a single instrument, MIRI, with also possibility to do imaging, to do coronagraphy, and also to do spectroscopy. So these instruments are really complex instruments. I think it's the first time we have so complex instrument, and there are 17 possibility of observation, 17 observing modes. So a short zoom on MIRI, because it is an instrument I have been working on since 25 years. It was a long road. It is a collaborative effort between ESA and NASA. And we had in Europe, we have designed and developed the optomechanics. And the US contribution was the detectors, the focal plane detector, and the cryocooler to cool MIRI. The European PI is Gillian Wright from the Royal Observatory at Edinburgh, and the US PI is George Rickey at the University of Arizona. And I am the French co-PI of this instrument. Just a zoom on the French contribution. The French contribution was what we call the MIRIM part of the MIRI instrument, that means the imager of MIRI with 3 observing modes: the classical imaging, high contrast imaging, and low resolution spectroscopy. So each instrument see part of the focal plane of the telescope. So we can observe with them simultaneously, but they don't look at the same part of the sky. So you have images with near spec, with near cam, with a PHY guidance sensor, with the nearest instrument, and with MIRI. You have an idea of the field of view of each of the instruments. And the result of the commissioning is that the image quality is better than the requirements. The requirements was that the image quality to be limited by the diffraction. The diffraction is, you cannot be better than the diffraction. That's a physical effect which limit which gives the size of a point source through your optics. And the requirement was to be diffraction limited at 2 microns. And in fact, it is diffraction limited at 1 micron, which is much better. The transmission is also better than requirement, again, because there have been very little contamination. Care was taken not to contaminate the optics, and that's payoff because we have really a very good transmission. Another important aspect is the telescope stability, which is really important when observing exoplanets, transiting exoplanets. And here again, the observation of the performances are much better than required. It's less than 1 milliarcsecond when the specification was 4 milliarcsecond. Just here, one image I really like is an image of MIRI on the right at 7.7 micron, and a comparison of this image with the image of the same field with the previous telescope, the Spitzer telescope. And you can immediately see how the performances in terms of angular resolution and in terms of sensitivity has been improved. I was really amazed when I made this comparison. If now we are more quantitative in terms of sensitivity, so you can see on this figure the wavelength range, from 1 to 10 micron. And this is the sensitivity in terms of our Jansky, in terms of Jansky, and a signal over noise of 10 in 10 to 4 seconds. And you can see compared to what was possible previous to James Webb, at least 1 order or even 2 orders of magnitude better in terms of sensitivity. So with such sensitivity, it is clear that there will be really new and surprises in various fields of astronomy, and it has started, as you will see. For some sensitivity, you have the requirement. For example, for NIRCam, it was 11 nanojansky, and in fact, what has been measured is 7. So the sensitivity, because of telescope quality and so on, are better than expected. It is the first time I see that for a space mission. I have seen several space missions, and we are really happy when we reach the requirement. But when we exceed them by almost a factor of 2, that's really exceptional. So what are the scientific teams with the James Webb? So it is an observatory. We have to ask for time, and there are committees which give you or don't give you the time. There are a lot of pressure. That's much more time requested than possible by a factor of 5. So there are 4 main themes. First, I just at the beginning introduce first light and reionization as one of the 4 things. Then you have the evolution of galaxies, the assemblies of galaxies, the birth of star and protoplanetary system, and the planetary system themselves, and the origin of life. So let me give you some insight about why observing in the infrared. So I have already mentioned the reddening of the light before the expansion of the universe. You have also the fact that with the infrared, you can look through clouds. This is on the left, you have a region of the sky observed in the visible, and you can even see some region of the sky if you can see the Milky Way, where you have dark clouds. Once you look in the infrared, you can see that behind these clouds there are a lot of stars. And to observe star formation, you really need to go in the infrared. So that was the second way why we are to observe in the infrared. The third reason to observe in the infrared is when you want to detect the emission of objects at relatively low temperature. So on this plot, you have again the wavelengths, the spectral radiant emittance in square meter micron. And you can see that according to the temperature, the peak of the emission evolve, and at lower temperature, for example, 500 Kelvin, you are in the mid-infrared domain, especially even if you are at 300 Kelvin, like the Earth. So the peak is around 10 micron. So if you want to detect such an emission of a low temperature object, for example, exoplanet, as that we did, you will see that in a moment, you need to go in the infrared. The fourth example of why we need to observe in the infrared is that the molecules have feature in the infrared, and it is used in many environments, in the interstellar medium, for protostellar disk, for protoplanetary disk, and for exoplanet atmosphere. You have in this table the various molecules expected in the atmosphere of an exoplanet, and you have the wavelengths where you can see a feature of this molecule. And it is in the infrared, near infrared, mid-infrared. And on this figure, on the right, again, the wavelengths and what you can expected in terms of transiting exoplanets. So Hubble was only probing a small region in the visible infrared. And with James Webb, you will be able to have diagnostics of all these molecules, water, methane, CO, CO2, NH3. So a lot of diagnostic will be provided with spectroscopic observation with James Webb. So in the 12th of July, 2022 was a great day for all those who have spent years developing the James Webb and its instrument. It was the first public release of, it was a deep field, and it was presented by Joe Biden, the US president. And in this image, you have already galaxies which are further away than those in the Hubble deep field. So only with 6 hours of observation, you do better than HST as well, which is what was the aim of James Webb, of course. So you have also some galaxy evolutions. And here it was the French president, Emmanuel Macron, who was at the NASA, and they show him mirror images of 2 galaxies in interaction. I think you will learn more about that by David. So just to show you, but you have already seen that, but all these nice images from nebulae. And I was myself really amazed how much detail. Zoom, and you see details and details and details. The image quality is really excellent. And of course, all that is important for all the study of and other nice nebula that you have already seen. Here is the Lyra Nebula around All Star, and also our solar system planets, some of them at least, will be observed with James Webb, as Jupiter here. But what I would like to concentrate now is on the exoplanet subject. 25% of the time has been allocated to exoplanet observation. On the left, you have one image of the HR 8799 system, the 4 exoplanets. It was the first time that they were observed in the mid-infrared. So we were able to do some direct imaging observation of exoplanet with James Webb. But I will not detail these observations, which were done with a coronagraph, because most of the results will come and are coming when we are doing some transiting observation. So let's just remind you, for most of you, just remind you that we have now detected more than 5,300 exoplanets, and the 2 key words are diversity and ubiquity. We see exoplanets that we don't see in our solar system, Jupiter, So inflated Jupiter, super Earth or mini Neptune, and so on. So really, that's a field in full progression. This is to illustrate this diversity. So you can see that there are small planets, big planets, and so on. And but James Webb will not be an additional facility to detect exoplanets. James Webb is a unique facility to characterize exoplanet atmosphere. And really, thanks to James Webb, we are fully entering in the second chapter of exoplanet studies, which is a characterization of their atmosphere. There are some niche program to detect exoplanet. I am in one program about looking in planet around a nearby star, but it's really a niche program. Most of the programs are dedicated to characterizing exoplanet atmosphere. What can you observe in this atmosphere? Of course, what we can do is determine the molecular or atomic content of the atmosphere, the presence of clouds, hazes. We can determine the pressure, temperature profile, the dynamics in the atmosphere, if there are winds, the variability in terms of weather, for example, and so on. And why do we want such information? What can we do with such information? Of course, there is the question of modeling this atmosphere, and it's particularly important to model in systems which are quite different from the planets of our solar system. So the physical, the chemical processes that work in such atmosphere, the formation of cloud, climate, dynamics, all that can be inferred from our observation of this atmosphere. The molecular content can also give some constraint on the formation and evolution of these exoplanets. And there is a link between interior and atmosphere, interior of the exoplanet and atmosphere, and you need to have constraint on the atmosphere to really have information on the interior. And of course, the ultimate goal, aim, would be to find biosignature. But I don't think we are close to find biosignature because we don't know yet which kind of biosignature we want to find. And the first step, and that will be what James Webb will do, is really to know the physical and chemical processes at work in this atmosphere. So let's go through the transiting of exoplanets. So I think all of you know that when an exoplanet transit between us and the star, you have a faint decrease of the emission from the star, and from that you can deduce the radius of the exoplanet. We observe a giant exoplanet with James Webb, WASP 39b. So you have a spectroscopic observation. So here again, the wavelength from 3 microns to 5.5 microns. And here is the amount of light brought. And you have at the position of the CO2 feature, you have an increase of the amount of light blocked because you have light blocked by the CO2. This was great, but it is something which has been predicted. This is a prediction. So again, wavelengths, transit depth is in this case, but it's about the same. And you can see that the model were predicting a CO2 feature. So it's good that the model can predict, but it's even better when there is a surprise. And the surprise was that around 4 microns, you had another feature which was not predicted. And it took some time to find out where does it come from. And after some theoretical studies, the solution has been found. It is, we had to add in the model what we call photochemistry. That means the photon from the star influence the composition of the atmosphere, because with UV photons, they can dissociate the high atmosphere water, and there is a whole chain of reaction which at the end give SO2. So it was the first surprise we got on the atmosphere of exoplanet. What is very good is when you can also make prediction, and the prediction was you should also have feature, SO2 feature, in the wavelength range of the MIRI instrument. Here you have again the transit depth as a function of wavelengths, and you can see 2 SO2 feature predicted. And in fact, this feature has been observed recently. It's I cannot yet show you because it's under embargo. And what is interesting when you can measure SO2 abundance is that you have constraints on the metallicity of the atmosphere, and then you can constrain planet formation. Metallicity means the number, the quantity of elements with higher than, different than hydrogen and helium. And the exoplanet form in this can, according to where they form, they have a different metallicity. So that's a new tool to constrain planet formation. Another example of finding is looking for the temperature of rocky planets with MIRI. So you have certainly heard about the TRAPPIST-1 system. This is a really cool star, small star, very small, at low temperature, and which is surrounded by 7 exoplanets, which have been detected by the transit method. It is a nearby system at 40 light years. Just to put this system in context, you have here the solar system with Mercury, Venus, Earth, and so on. And the TRAPPIST-1 system is here. So it's a really compact system. You have a zoom of this small region here. So the exoplanets around TRAPPIST-1 are very interesting because they have a radius similar to the Earth's mass, and then a density similar, which means that these planets are rocky planets. And some of them are in what we call the habitable zone, which is just to say that the water can be in a liquid form. For those who are close to the star, the water is in vapor form and too far in ice form. So it is important to know what is the temperature of this object. So just to give you some context, these planets are old planets and they are heated by the star. their temperature come from heating from the star. They are heated and they are radiated. So the observation, we observe TRAPPIST-1b, the closest exoplanet to the star, during 5 eclipses and with the MIRI filter at 15 microns. And we detected the emission from the exoplanet. This has been published in Nature a few weeks ago. How find this flux was just by measuring the flux before, during, and after the eclipse. We just had the flux before and after divided by 2 and remove the flux during the eclipse when we had only the emission from the star. And there is a tiny difference of 0.1% that we were able to detect. And you can see here, so this is as a function of time. So this is before eclipse, and you can see during eclipse and after eclipse. So you can see the dip when the emission from the exoplanet was hidden by the star. From this, we were able to measure the temperature of the exoplanet. And we measure a higher temperature than predicted. It was predicted to be at the level of 400 Kelvin, and it has been measured at the level of 500 Kelvin. How to explain that? So we have to take into account that the TRAPPIST planets are in synchronous rotation. That means that during one rotation, one orbit period, one turn around the star, there is one rotation of the exoplanet itself. Always the same face, the same part, which receive the star light. And if there is no redistribution of the energy on the hidden part, then you have one hot phase and one cool phase. And if we say all the energy of the day side stay in the day side, then you can account for the measured temperature. What does it mean? It means that there are no or little atmosphere, because the atmosphere with wind, for example, can transfer the energy from the day side to the night side. So it means that 1b is a bit like Mercury with no atmosphere. We will have other observation in July, again for TRAPPIST-1b with another filter to confirm or infirm this first conclusion. TRAPPIST-1c has been also observed, and it has been, the emission has also been detected. It has just been accepted by Nature, so you will hear about that in a few weeks. And we are proposing additional observation. You know, observing with the James Webb, you ask for proposal every year. You can ask for proposal, and you get or not you get it. So we have asked to observe TRAPPIST-1b and 1c, but not only during eclipse, but also during a full phase, during a full period, orbital period. And with this, we expect to be able to measure the night side temperature to confirm or not our first finding. There are also other very interesting exoplanets to be observed, like lava planets, which are so hot that the rock is melted. And it could be a way to see how the Earth was at its beginning when it formed. Should have been very hot. Another very interesting rocky planet to be observed is LHS 3844, where we know there is no atmosphere, so we will observe the rock. We observe the rock composition, so it is geophysics. To finish, I just would like to mention to you a project which involves non-professional astronomers. It is called ExoClock. It's to determine the ephemerid of exoplanets in the framework of the next future exoplanet mission, the Ariel mission. It's an ESA mission to be launched in 2029, which will observe 1,000 exoplanet atmosphere. It is dedicated to the observation of exoplanet atmosphere. And it is important to really follow the evolution of the ephemerid, because the uncertainties we have at the moment is too high to be sure at what time will the transit be observed in 7 years from now. So if you are interested, it's really an open project. I have just put there the website. So to conclude, I would say that James Webb is working, which is, I consider, normal. It has been a very long road, and it has costed much more than expected. It's now from $1 to $10 million. But what is really exceptional is the exquisite performance, better than specified, and at the best we could expect. And also the possible long lifetime opened by the perfect launch by Ariane is really, really very promising. So we have got the first surprises. I mentioned some results on the exoplanet, and David will mention the surprises in terms of first light and galaxy evolution. Thank you for your attention.
Thank you. If anyone has a question in the chat, we can relay it. I don't know, you can ask in the chat.
So yes, we have a question from Anaklu, who is asking, he said, I'm interested by the papers of the camera performance we saw in the presentation. Is it possible to have a link or something? Thank you.
Yes, I can find it. It is on ICAY. I don't know if you know ICAY. I can, if you give me your email address, maybe in the chat, I can send it to you.
Maybe send it to Alexander, and then
I will send it to Alexander. Yeah.
No
okay,
problem.
Thank you.
Is any other question? No? I'll just wait a few seconds for the delay. Okay, so thank you, Dr. Lagage, for your insightful presentation. Ladies and gentlemen, we'll now take a 5-minute break. When we return, we'll be joined by Astronomisk Ungdom and Marion Zannese from the Institute of Space Astrophysics. Please take this opportunity to stretch your legs, The staff will be pleased to answer any of your questions in the chat room, so please do not hesitate. Keep in mind that the description contains the program of our Congress and other useful informations. We'll resume this stream shortly. Thank you.
the break is over, so let's travel a bit and talk about the Swedish organization. So it is an association that promotes the interest of young people in astronomy. And when we talk to this Congress today, it was born from our meetings with their association. So that says a lot about what we can do together in the future. So I would like to introduce you, Astronomisk Ungdom. So sorry for my Swedish accent. I have so much to learn. So you.
Thank you. Do you guys see the presentation?
Yeah, perfect.
Okay, great. So thank you again for introducing me. And I am from the Swedish Astronomical Youth Association. My name is Asti, and I'm vice chairman for this organization. So we started this collaboration quite newly. So this is, I think, in a way, our very first collaboration as well. But our organization was established back in 2012, and we've grown a lot since then. We've been going for almost 11 years now. And this is a brief map of how we do our work today. So we have the AA board, which is where I am, and together with the rest of the team, we do a lot of the strategic work. It could be everything from governing documents to new collaboration programs, looking for the future opportunities for our members, and doing other stuff like yearly budget and sponsorships. Then we have our office, which is where I am at right now, and they work with the yearly programs we have for every year. So you could, in a way, explain it as we have two different branches. One is the members themselves and what they are doing, and then we have the national operations we are doing. So for the members themselves, they are usually spread all over Sweden. We have about 3,000 members today, but we are growing rapidly, and they are all in a different part of the districts that we have in Sweden. So they are members of smaller astronomy clubs, theme clubs, school clubs that are associated with our organization. So everything is astronomy correlated, and they are placed in a specific district, and the districts have themselves a board which works with financial support, finding premises, and arranging regional conferences, events, and such. So, and they are again connected to our board, so we work together with them. And then we have again the office, which works with our yearly programs that is for all the individual members, and that could be our rocket program, which is a new one, which they will be the individual members will be able to create devices or measurement devices that they might have the chance to send up to space. We have the ICAY cancer program, we have the Swedish part of it, and then we send the team to the international competition for that. And we also provide scholarships, astronomy competitions, and such. And we have, I think this is our most popular program, and that is for high schoolers, is the Science Summer School program. They have a full summer full with astronomy lectures with great professors, and they usually have a project they need to present at the end of it, which is more of a scientific research part of it. And it has a lot of connections with the ESA and rocket program that I mentioned before. And then we also create larger social events. We have met a lot of astronauts. We have larger conferences, lectures, and we also provide camps all around Sweden. And then a new branch is for the students and universities. So we want to include them as well and reach out and try to make more conferences that is more fit for them and so. And then, let's see, yeah, this is another brief example of what we are doing. So the middle part of the picture, or the middle up, is from the Science Summer School program here in Stockholm. And in the middle, you can see Max Tegmark, a really famous professor, together with the students. And to the right, you have Ulf Danielsson, another famous professor, which is also in the committee of the Nobel Prize winners in physics. So he's one of the guys that actually decides who gets the prize each year. He is a theoretical physicist. So this is an example of having him during one of our lectures, during our conference. And then we see a picture with the founder of the organization, with another one from the board. They are standing there with SSC, Swedish Space Corporation, and they are working on this was actually our very first Aurora 1 project. And the thing that Hugo is holding in his hands is actually a measuring device created during our summer school program from our high school kids. And that one was actually sent up to space with their rocket. So that was really cool. And that was during the critical testing period, I think. So that is one of the newer things we're doing. And then down there, you see our biggest, I think, conference or event. And that was us celebrating 10 years. That was in December. So that was just us celebrating and having fun. And to the left, you see one of our very famous trips we have each year. And for that specific year, we went to La Palma. So that is a picture from that trip. And then we have CANSAT students or participants that are building their mini CAN satellite from scratch. And we are helping them there to get further into the competition. So we do a lot of different stuff. And again, our goal and main purpose of everything is to be the centerpiece for young adults that likes astronomy and aerospace. So we just want to create more and more opportunities for them, both socially to find friends that are thinking more like them or having the same interest, but also to be able to, reach out to that sort of part of Sweden, but then internationally as well, to create more opportunities for them. And a new branch that we have, which is part of this collaboration, is our new international part. So we do have two main goals for this right now, and that is the ICAY La Palma telescope. So we are having this project where we're trying to, or in a few years, we will probably have a mini telescope at La Palma, which is part of the Canary Islands. And we want to be able to, again, give students more opportunity for research work and to have a nice trip and be able to observe stars in the universe and such. And then something that is more aligned with what we're doing right now is the European International Space Conference that we want to create. And so our plan is to gain a lot of members internationally, both for South John's, but in other countries as well, and try to bring together everyone at a bigger conference and trying to make more opportunities and having a lot of fun all together. So that is sort of what we're doing right now. Yeah, but that was it for me. Thank you for listening. And if you have any questions, I don't bite. It's just ask them. And if you want to contact us, you'll find the contact information down there. So that was it. No questions?
You have to wait a bit because there is a delay. So do not hesitate to ask them in the chat room, the attendees. During waiting for the questions, I have to introduce then. It is a great pleasure. So thanks to Asti. I have to introduce and I have to say that it's a great pleasure to welcome you, Marion Zannese, by continuing this conference series. So welcome. You are from the Institute of Space Astrophysics. The JWST is at the cutting edge research, and you will discuss your new results in this cutting edge field. So the attendees, we will relay your question live to Madame, so please do not hesitate to ask them in the chat room. So thanks you for coming, the floor is yours.
Good afternoon, everyone. I'm Marion Zannese. I'm a second-year PhD student. I'm working, so as Alexandre said, at the Institut d'Astrophysique Spatiale in Orsay, near Paris. And I'm specialized in the interstellar medium, meaning all the matter that is between stars. and today I'm going to talk about the impact of massive stars on stellar and planetary formation observed with James Webb Space Telescope. And more particularly, I will talk about the study of highly excited molecules in those environments where stars and planets are formed, which is my field of expertise. So first of all, maybe before going into the details of how massive stars are going to impact the formation of stars and planets, maybe it is a good opportunity to explain in a quick and easy way how stars and planets are formed. So you may know stars are formed in molecular clouds, which are a large structure in the universe. To have an idea of the size of these clouds, it's about 10,000 to 100,000 masses of the sun. So very big structures that are at the equilibrium, meaning that there are two forces on these clouds. One is making the particles go as far away as each other as they can, which is the thermal pressure, and there is the gravitational force that wants the particles to be as close as each other. These two forces in general compensate, but if there is a perturbation, this equilibrium can be broken, and that could lead to a gravitational collapse. Not all the cloud is going to collapse, only small fragments of these clouds are going to collapse, and this is what this video shows. So there's a perturbation going to change the structure of the clouds, and small fragments in the clouds are going to collapse on themselves, and all the white dots that you are seeing appearing in the video are newborn stars. So you can see that with the time scale you have on top, this is a phenomenon that takes a long time. This does not happen in a day. And in a single cloud, a lot of stars can be born. It's not only one star per cloud. That's why we often say that these are stars cluster, because stars are born in the same cloud. Once this collapse has happened, so that the newborn stars is born, it is not exactly yet a star. It is what we call a protostar, a bit like a baby star. And it is going to need a bit more time before achieving its adult form. What is going to happen is around this protostar is going to appear a disk of matter, a plane disk, that's going to be rotating around the star, and the star is going to accrete the matter from the disk. So it's going to accrete matter until it reaches its final form. But the remaining matter in the disk is going to aggregate on itself. And this is little by little going to create planets. At some point, there won't be any matter left in the disk, and that's when the planets are formed. There will be only planets rotating around the stars and void between them. That's generally the idea of what we have when we are thinking of formation of stars and planets. But that's maybe a bit too easy, because we are not taking into account the environment. By that I mean we are just saying, okay, the cloud collapsed, it creates a disk, and then we have stars and planets. But the thing is that the cloud is not in the middle of nowhere. It has other stars around them, other phenomena that could completely change the structure of the cloud. And if we don't take into account the environment, that's a bit of a problem. For example, the observations, we are not able to reproduce the observation with only taking into account these models. By that I mean we are producing 10 to 100 less solar masses, so mass of the sun, per year, as we should be if we just took these models into account. So that means that the environment have a huge impact on planets and stellar formation, and that we cannot neglect it if we want to understand the observations we are getting. So what I'm going to try is answer the question, what happens when we take into account the surrounding environment when it is the case of formation of stars and planets. And today I'm going to talk about a specific feedback, which is, as I told in the title, the feedback from massive stars, so radiative feedback. First, I'm going to explain how it will have an impact on star formation. So massive stars, which are about 10 to 30 times the mass of the sun, so really big stars, are going to radiate some UV field. And this UV field, as the stars are massive, is going to be very intense. And as it is very intense, it's going to completely change the physical and chemical conditions of the clouds nearby. And thus, it's going to impact the stellar formation. By that, I mean, the UV field radiated by these massive stars is going to create what we call photodissociation region. So this is the region at the edge of the cloud where the UV field is going to change things a little bit. So to explain you what is going to happen, you can see the eye, so where it is in the cloud. When we are at the center of the cloud, the molecules and the particles that are there are not feeling the UV field. A bit like when a cloud goes in front of the sun, you can't feel the sun as much as when there were no clouds. Here it's the same. The molecules at the center of the clouds are protected from the UV field by all the other molecules that are in front of them. So they can't feel anything. But the closer you go to the edge of the cloud, the more intense the UV field becomes. And this is going to have an impact on the molecules there. So at some point, the UV field is going to be strong enough, not attenuated enough by the other molecules, gas and dust, and it's going to break the bond between atoms. This happens at a region that we call dissociation front, because this reaction is a photodissociation. The molecules is going to be photodissociated, meaning the bond between the two atoms are going to be broken, and this is going to create only atoms. For example, in the case of the molecule of dihydrogen, H2, which is a very abundant molecule in a molecular cloud, this reaction is going to create 2 atoms of hydrogen. Once again, if we move closer to the edge of the cloud, the UV field is going to be even stronger, and this is not only going to dissociate the molecules, but it's going to ionize the atoms. That means that the electron and the atom are going to be separated, and we're going to have ionized atoms and electrons. This happens at the ionization front, so the front that separates the ionized region from the atomic region, and this is what we say is the end of the cloud. After, it's the ionized region, or H2 region, H2 for ionized hydrogen, and after that we consider it's not in the cloud anymore. So you can see that the UV field emitted by this massive star is going to completely change what we have in the cloud. And this is not only going to change the chemistry, so the particles are there, it's also going to change the physical condition. Indeed, by all this reaction, what is going to happen is that the UV field from these massive stars is going to hit the gas. To have an idea of how much it can hit the gas, you have to think that at the center of the cloud, the temperature is expected to be 10 to 20 Kelvin, so very close to the absolute zeros, which is about minus 260 degrees Celsius. So it's very cold. But when there is massive stars irradiating this kind of region, the temperature can go up to 10,000 Kelvin, so a lot higher. And this variation of temperature is going to be very quick. The temperature is going to change very rapidly in this small region at the edge of the cloud. As it is hitting the gas, it is also going to disperse the gas, meaning that the density in the cloud and outside the cloud is going to be very different. We can have maybe about an order of magnitude between the center of the cloud and the outside of the cloud, so about 10 times more. The cloud is going to be 10 times denser than the outside of the cloud. So in the H2 region, the particles are going to be very far away from each other and are going to move very quickly. And finally, as I told you just before, the UV field is going to ionize the gas. So not only it's going to change the physical conditions of the gas in the cloud, it's going to completely change the properties of the gas. All of that, you can maybe already understand that it's going to limit this stellar formation. Indeed, as the gas is hotter and less dense, it's going to be more complicated to make it collapse and create a star. The particles won't want to go all together because they are moving very fast or far away from each other, and it's going to be very complicated to collapse. If there is no gravitational collapse, there is no stars. So this feedback is going to limit the formation of star. Let me be sure that I'm well understood. It's not I'm not saying that no stars are going to be formed in those regions. They are still going to be formed. It's just going to be more complicated and slower. That's why the observations show that we are not producing enough stars every year, because there are some of this feedback that are going to stabilize the clouds and preventing from collapsing. So I told you about how it is preventing the stellar formation. Well, will it have an impact on planet formation? Is the radiative feedback only have an impact on stellar formation, or can it have an impact on planet formation? Well, actually, it's a bit more of a specific case, because it will only happen in those very irradiated regions. As I told you, the UV field is going to limit the stellar formation. That does not mean that stars are not going to be born anyway. But if stars are born in those regions where the UV field is very intense, that means that there are some protoplanetary disks, so the disks where the planets are from, are going to also be in those regions with a very high UV field. And if the clouds can feel the UV field, you can understand that all the objects that are going to be in the cloud are also going to be impacted by this UV field. What is going to happen there is that the UV field is so intense that it's going to have the same impact on the protoplanetary disk than it has on the cloud. So it's going to heat, disperse, and ionize the gas. But the thing is that it's going to do that from the disk, and this gas that's going to be heated and dispersed is going to go out of the disk. So the UV field is going to deplete the gas from the disk, meaning that there's some matter that was in the disk that is going to go outside of the disk. It is then easily understandable that it is going to limit the formation of planets, the same way that it was limiting the formation of stars. Because if some matter in the disk is taken away because of the UV field, it is some matter that was supposed to create planets. So if it's not there anymore, the planet is not formed. So sometimes in this case of externally irradiated disk, some giant planets that were supposed to be formed will not be formed because of this mass loss from the disk. The UV field is then creating what we call the photo-evaporating wind, because the matter from the disk that is taken away is getting photo-evaporated. And this is what we see on this figure. The gas bubble around the disk is the photo-evaporated wind. And what is really great is it's going to have the same transition, the same regions that I talked to you about in the photodissociation region, so PDRs, with the ionized region, the atomic region, and the molecular region. So it's going to act very similar to a PDR, which is going to be great for us to understand what's happening there. You may understand now why these regions are the target of numerous James Webb Space Telescope programs. Because these regions are so rich and so important to understand really what's happening in stellar and planet formation, that's why we want to understand more about them. To have an idea of how important these regions are, you can see that two of these regions irradiated by massive stars, like the Carina Nebula and the Tarantula Nebula, were used by NASA to be the first images released on the 12th of July 2022, to show that these regions are so famous and important in the community that they were chosen to show the first results of the James Webb Space Telescope. They are also the targets of GTO program. So GTO is a guaranteed time observation. That means that the people that are in charge of this observation will have the data private for them for a year. This GTO is focused on two PDR, which is NGC 7023 and the Horsehead Nebula, the horsehead because it looked like a horse head. And this program is focused on these two regions to understand more about PDRs. There are also an ERS program, so Early Release Science, which is meant to produce a scientific tool for the astrophysics community. It has the advantages to be priority to all the observations, meaning that it's going to be taken in the 6 first months of activity of the James Webb Space Telescope, and the data are going to be public for everyone. This ERS, I will talk about it later because this is the program of observation I'm part of. I did not put there all the multiple programs there are on disks because they are not automatically on externally irradiated disk where we can see the radiative feedback. But there are so many programs focused on disk and survey of different disks in the universe that it is for sure that they are going to be in their survey externally irradiated disk. We are going to bring even more information on those regions. And finally, there are also going to be a lot of future observation proposals to have even more data on those regions that are still revealing and hiding a lot of mysteries from us. I'm pretty sure that during this Congress, we have already described the James Webb Space Telescope for you, but I prefer to redo it with you to be sure that everyone understands why it is revolutionary and why, in specific to my field, it's going to bring even more information that we have already gotten in the last few years. So the James Webb Space Telescope is a telescope with a primary mirror about 6.5 meter diameter. This is the largest telescope that has ever been launched into space. It looks in the infrared, so its wavelength range is from 0.5 to 28 micrometers. Fun facts, we often say that the James Webb Space Telescope is the successor of Hubble. I do agree about that when we are thinking about goals, meaning it is the successor of Hubble if we think about the size of the project, the ambition of the project, and the revolutionary aspect of the project. It is kind of false if we think in a physical sense, because Hubble was looking in the visible wavelength, so in wavelengths that we are seeing every day, the colors that are seen visible to our eyes. This means that even if Hubble and James Webb are going to produce similar images, it's going to reveal a very different physics. And the infrared is particularly interesting when you are studying PDRs or protoplanetary disk, because this is the wavelength range where the most of the emission of this region are. So this is very important to have a telescope that is looking in these wavelengths, because this is where we have the most information on the chemical composition, the physical conditions of this region. Then it has 4 instruments. I'm going to go quickly on them because I'm sure you have already been told about them. It has a camera, a near-infrared camera, which is NIRCam. So all the very beautiful pictures that you've seen on the internet from James Webb are from this instrument. These are 2 spectrographs, one in the near-infrared, so low wavelengths, and in the mid-infrared, so longer wavelengths. And the mid-infrared instruments also have an imager to also provide some pictures. It is good to know that MIRI, the mid-infrared instrument, is one of the instruments that was made in France in collaboration with different laboratories, so ICAY, Observatoire de Paris, Paris Observatory, and Institut d'Astrophysique Spatiale, the laboratory I'm in. And finally, it has also an instrument to guide the telescope. Why it is so revolutionary and why the James Webb Space Telescope is so important to the astrophysical community? Why are we talking about it so many times? And what is it going to bring for astronomers in terms of science? I think the main response to that question is its spatial resolution. So the spatial resolution is the ability of a telescope to separate 2 points in the sky. So if 2 points is at a certain distance, what is the quality of the telescope that's going to be able for us to see 2 points and not only one? With its very huge mirror, so we said 6.5 meters, the James Webb Space Telescope has a very high spatial resolution. So it's going to be able to detect and resolve very small objects. And this is essential in my study because, as I told you, I study protoplanetary disk, which might look big for you because you say protoplanetary disk is the size of the solar system, pretty big. When this protoplanetary disk is at great distances, so about 1,000 light years, it's going to be very small. And if the spatial resolution is not high enough, we might not be able to detect them. So when we want to study protoplanetary disks that are great distances, we need to have very high spatial resolution to be able to detect them and have a good view on this. These are large structures, so we might think it's not that important to have high spatial resolution. But as I told you, the physical condition in those regions changes very rapidly, meaning that the change in temperature is going to be at very small scales. So if we want to have information on everything that's happening at all the stages of this variation of physical conditions, we need to have high spatial resolution to be able to resolve them. So to study all the small scales of this region, we need to have a very high spatial resolution. The second argument of why the James Webb Space Telescope is revolutionary is its high sensitivity. It's going to be able to detect very, very faint light. And for me, that is particularly interesting because I did not go into the subject yet, but as I told you, I studied the high excitation of molecules. It may be difficult to understand, but let's put it that way. If the excitation is high, it means it's difficult to excite this molecule at this level of excitation. That means there are not a lot of molecules that are going to be excited at this level of excitation, which means that the lines that are going to produce going to emit is going to very need into
Okay, excuse me everyone and excuses. She looks like to have some connection problems, but it should come back. Hi, Marion. For about a minute, I believe, we were not hearing you very clearly. So
sorry.
may you start back, please?
When do you want me to start back?
Maybe like a minute ago. About when the last slide, in fact, it could be good, I believe.
So this slide, I don't know where you lost me.
Yeah, this part, like the last point, essential to detect new highly excited species.
Okay.
Thank you.
So to recap what I was saying, the second argument of why the James Webb Space Telescope is revolutionary is that it's going to be able to detect very faint lines, very faint light, and it is essential with the study of highly excited species because, as I told you, the excitation of this molecule is going to be very difficult. So that means that there are not a lot of these molecules that are going to be this excited, which means that the light they're going to emit is going to be faint because as they're not very abundant as other species, their light are going to be fainter. So if we want to detect them, it's going to be very important to have a high sensitivity to be able to detect them. And that's kind of the goal because with all the other observation, we already have access to a large number of molecules, species, lines. So if we want to detect something new, we're going to have better instruments. And this quality of a high sensitivity is very good to learn some more physics about these regions. So I hope I convinced you that the James Webb Space Telescope is really revolutionary. And now I'm going to talk a bit more about my program of observation. So this program is called PDRs for All. As I told you, it's an early release science program, so the data are public and we are expected to provide some tools to the scientific community. This program is led by 3 people, with 2 French people at the head. One of them, Emilia Barr, is my PhD supervisor. This program is composed of an extended core team with about 50 people from all over the world with very different domain of expertise. But we also have collaborators. More than 100 scientists from 18 different countries are helping us understand the data. And even though they are not working on a day-to-day basis as the extended core team does on this data, they are still essential to be able to understand this very rich data and the large amount of data that we have. This program is was observed in September and January, about 40 hours of observation, and it is using all the instruments of the James Webb Space Telescope. Let me talk a bit more about the team. As you can see, we have people from all over the world. Half of the people are European, but we have a third of the people which are Americans, and really from all over the world. So Asia, South America, Canada, really from everywhere. But what I want to really stress on is the variety of the expertise of the people in this program. You can see that more than half of the people are observers, meaning we are specialists of analyzing data and understanding them. In this 60% of people, there are people that are essentially doing the data reduction, because when we first receive the data, the things that the James Webb Space Telescope is sending us is really not usable to do science. We need to shape it and make it okay for us to have sensible information and data that are usable. We need to calibrate it, we need to subtract the noise and do everything. And the rest of the people are the ones that are specialists in diagnostic, for example, so on molecules, for example, for me, on dust, on ionized gas. So everyone has something to do in this observation program. What I also want to stress on is that even if 60% of the scientists are observers, more than 40% are not automatically astrophysicists. Indeed, some people are doing theory, so theoretical models, so quantum calculation or models to predict the data that we're going to be able to see, make models for us to understand the observation, but also predicts what could be seen with the James Webb Space Telescope. And the second 20% are people doing laboratory experiments. So yeah, even in astrophysics, there are some people doing experiments where they are trying to reproduce the physical condition that we have in the interstellar medium, or at least they are trying their best to reproduce the condition, so that we can reproduce the spectrum we are getting from this region, and helping us understand what we see. Because when we detect new molecules, it's difficult to be sure what molecules it is. So it's important to have both laboratory experiments that could reproduce the data and also theoretical experiments that could explain what is happening behind this spectrum. This program is focused on a very famous photodissociation region, which is the Orion bar, which is located in the Orion Nebula, which is at below the belt of the constellation of Orion. This is a region of formation of star which is very close to Earth. That's why it's a very famous photodissociation region. It's only 1,500 light years from Earth. So that's pretty close. Once again, even if you think that's far away, at the scale of the universe, it's very close. And in this region, at the center, we have some gas that is irradiated by the trapezium cluster, which are composed of massive stars, and create this photodissociation region, which is sorry, in the shape of a bar. That's why we call it the Orion bar. As it is very close to Earth, and it is even visible, the Orion Nebula is even visible in winter in France, if we have a very dark skies and some nice goggles to look at it. This region has been observed a lot throughout the year. For example, here in 2000, we have some observation to try and detect the structures that we could see in the Orion bar. You can see that we have something. It's really difficult to understand what is happening there. And it is quite extraordinary to see how fast we advance in the observing techniques, how fast we are improving the images we can get from new instruments. For example, in 2016, the same region was observed with ALMA, the interferometer in Chile, and we can see that, in fact, the PDR is a lot more structured than we had expected to. It has completely revolutionized our view of PDRs, and we can see that, in fact, there's a lot of filaments, sharp edge of the cloud, globules, some very light structures, and we understand that it's a lot more complicated than our first view of PDRs were. In 2022, we have been able to observe the same region with the Keck telescope in Hawaii, which has an adaptive optics, which can make it have a very good spatial resolution. So you can see the improvement on the quality of the image, and you can see that all the structures that were once seen are now resolved. And this is going to be very good to do a lot of physics on this region. What is great is that the Keck telescope has a spatial resolution close to what the James Webb has, so it was a bit of a preview of what the James Webb Space Telescope could do. I've told you that the real predecessor of James Webb Space Telescope is not Hubble, it's Spitzer. So here is an image of Spitzer of the Orion bar, and you're gonna look for yourself of the improvement of quality in the image at the same wavelength. So now, since September, the Orion bar, which once looked like that with Spitzer, now looks like this. You can see that we were missing so many information with only the Spitzer data, because we had the general shape of the Orion bar, but we didn't have access to all the structures that can be seen below the Orion bar. We didn't have access to all the small objects that they are hidden in the Orion bar. So that shows how in a couple of years we have been able to improve our techniques to observe the Orion bar. To have another image with different colors for you to understand what is really seen in these regions, you can see that the Orion bar is in fact very structured, and with the James Webb Space Telescope we are able to resolve all these structures to understand the exact structure of the Orion bar. So this is what happens at the dissociation front. But what is really nice is that in the Orion bar we can also see a protoplanetary disk, so the small bump that you can see there, that is also irradiated by the massive cluster of the trapezium, by the trapezium cluster. So I told you that these regions are particularly interesting to study because they are the place where the radiative feedback happens, and it is important to understand the formation of stars and planets. Maybe I'm a bit biased because I'm doing chemistry with the highly excited molecules, but it is not only for that it is very interesting. It is also very interesting because it can act as an astrophysical laboratory. In fact, the Orion bar, this position is a bit inclined, so it is what we say edge on. That means that we can see all the regions that I talked to you about at the beginning of this presentation are seeable. We have the ionized region there, the atomic region there, and the molecular region here. So we have access to very different regions with their very different physical conditions. The ionized region will be a hot region, the atomic region will be a warm region, and the molecular region will be cold region. We also have access, as I told you just before, the presence of a protoplanetary disk in the same field of view. With the same condition of observation, so with one single observation, we have access to very different regions, different objects, because even if I told you that PDR and disk are kind of similar, there are still very different densities, very different structures, so we're going to be able to see how molecules are going to act differently in different regions. So to conclude, you have to understand that in a single field of view, we have access to very different chemistry at very different temperature and density. So it's going to be perfect to understand the chemistry in the interstellar medium, because everything that could happen, most of it actually is happening in this field of view. So I hope I've convinced you on how the Ariane bar is very interesting to study. Now you may wonder, why do I study highly excited molecules? I told you that the chemistry is very rich, there are a lot of different species, a lot of different physical conditions, so why do I focus only on highly excited molecules that are producing very faint lines that are difficult to detect? Why do I bother with these molecules? Well, first of all, why do I bother with water, OH, CH+, and H2? So first of all, for OH and CH+, their formation reaction is kind of difficult. So OH is formed via the reaction of O plus H2, and CH+ is formed via the reaction of C++ H2. So these two molecules are very similar in the way they are formed. But you can see just at in the right that there are energetic barrier. I put the energy in Kelvin because in the interstellar medium we can have an equivalence between temperature and energy. If the temperature is high enough, it means that the gas has enough energy, has a certain amount of energy. So we do this equivalence and we often talk in temperature. You can see that this energetic barrier are about 30,000 Kelvin, which is a lot. I remember you that at the beginning I told you that in this region the temperature varies from 10 to 10,000 Kelvin, really at the edge of the cloud. So that means that where I studied these molecules, it's about 500 Kelvin, maybe 1,000 Kelvin, not more. So this energetic barrier are a lot higher than the gas temperature. This means that it's going to be very difficult to form them, and it's going to only trace dense and warm environment because that's the only place that are going to be able to be produced. And as I told you, as the physical condition changes very rapidly, that means that it's going to trace very localized regions. So that's super interesting if you want to have information on a very small scale. The second argument to why these molecules are so interesting is that the excitation in the near and mid-infrared, so in the wavelengths where the James Webb Space Telescope is looking at, it's going to be very difficult for them to be excited at these levels. It means that the levels that they need to be excited to de-excite and produce lines in these wavelengths are going to have very high energy, a lot higher, once again, than the gas temperature. So it means that it's going to be very difficult to excite these molecules, only taking into account collisions in the cloud, which is often the case with other molecules. They're excited by collisions. That means that the excitation of these molecules is out of equilibrium. That means it's non-collisional. That something else is exciting these molecules at this level of excitation. And that's often very interesting because that unveils a lot of microprocesses that are a bit complicated and that are very beautiful. And it is going to give us access to different things than only the abundance of these molecules. It's going to give access to a lot of the physical condition of the cloud. For example, one of these processes is the photodissociation of water. When the UV field is going to find a water molecule, it's going to break the bond between the oxygen and the hydrogen, and it's going to create OH plus H. The fact is, when this reaction happens, is going to create OH in a rotationally excited state. That means that when the bond is going to be broken, OH is going to rotate on itself. And this energy that it has, it's going to wants to de-excite. By that I mean, OH is produced in a very excited rotational state, so it's going to rotate on itself very quickly. The levels that it reached are about 40,000 Kelvin, so 100 to 1,000 times more than the temperature of the gas. Very excited. This could not be excited by anything else than these very specific processes. Once it's created, so it's already excited, it will want to de-excite to reach the steady state. So it's going to cascade throughout all the levels of the molecules, and it's going to produce photons every time it's going to cascade. This is going to produce lines in the mid-infrared. And that's nice because that's exactly the wavelength range that is in MIRI. So we hope that we could see this line in MIRI. You can see here the spectrum of OH. When we don't take into account the photodissociation of water, you see that all these lines in the mid-infrared is not there, meaning that only this process can excite OH at these levels and produce these lines. This is very nice because these lines are going to be proportional to the quantity of water photodissociated by unit of time. Indeed, the OH produced in this rotationally excited state is due to the UV field that is going to photodissociate the water and the molecule of water that is the molecules that are going to produce water after the photodissociation. And that is very nice that this is directly proportional, because that means we have access on either the UV field. By that I mean if we know very well the quantity of water in the regions, if we detect those lines, we're going to have an information on the UV field. We're going to be able to constrain it very powerfully. And vice versa. If we have a good information on the UV field in these regions, that means we're going to have an information on the quantity of water. And that is even more stronger because we could be in a case where we don't detect water, but if we detect those lines, that means that there are water, because if there were not water, there would not be these lines. So we could derive the quantity of water without even detecting water. So that's a very strong process. These lines have already been detected in other objects such as outflows, so jets from protoplanetary disks, but they have never been detected in PDRs before, so that's why I really hope that we will be able to detect them in the data. To be sure that we could detect them, we often talk about the data of the James Webb, but we don't talk enough about all the preparation that were before the data arrived. That means that for a year, so during my first year of PhD, I made models to understand where we could be able to detect those lines other than in the outflows. So I'm not going to talk about all the modeling I've done because that would take too much time. But if you have any question, you could ask me at the end of this talk. But I'm going to present these figures that kind of summarize it all. Here I've traced the intensity of these lines as a function of the pressure in the cloud and for different incident UV field. And you see that for 4 orders of magnitude in pressure, we can increase the intensity of this line by a factor of 1,000,000, so pretty much. But that gives us great constraints on the regions that could be able to produce these lines. This means that we need regions with high pressure and high UV field. If both of these conditions are not fulfilled, that means we could not detect these lines with the James Webb Space Telescope. That gives us not too much candidates, actually. For example, the Herschel Nebula, the pressure is too low, the same with HSC 7023. So that means the only candidate that is probably going to be able to produce this line is the Ariane bar, and also protoplanetary disk, which is also at the same kind of pressure in the Ariane bar. So that's one of the processes that are very beautiful and are going to help us have a lot of constraints on the iron bar. It is not the only one that I'm studying, and I can talk about a second one of this out of equilibrium processes that are going to give us a lot of information on the physics that is happening in this cloud. For example, I've told you that OH and CH+ are formed via this reaction. What we think is that maybe this reaction could produce OH and CH+ already in a vibrationally excited state. So I had told you from the photodissociation of water, OH is going to be rotationally excited, so it's going to rotate on itself. Here, the excitation is going to be vibrational, so the bond is going to be extendable and it's going to vibrate on itself. This is due to the fact that H2 in this region could be excited because of the huge UV field, because of the density. H2 could be excited. It could be vibrationally or rotationally excited. And what happens is that when it meets an oxygen or a C+, during the formation, the collision of these two particles that is going to create OH or CH+, the excess of energy that H2 is bringing is going to be transferred to the product. So that some of the energy that H2 is bringing is going to help to pass the energetic barrier just to form OH, and if it is enough energy, it's going to even produce OH in an excited state. That is really nice. So that is really nice because it's going to produce OH or CH+ in excited vibrational states. That means it's going to produce other line because once again it's going to be de-exciting through some lines, and these lines are going to be in the near infrared, so it may be detectable with near spec. So these two processes are going to be very interesting because we're going to be able to see two different processes of excitation of OH or CH+ in both the near infrared and the near infrared, and this processes is going to be bringing even more information. Once again, it's not going to be related to the quantity of OH or CH+. That means it can have very low abundance of these molecules and still have very bright lines, because all we need is the excitation of these molecules. So it's going to bring, for example, information on the density and the temperature, but more than just bringing information on the physical condition, it's also going to unveil the chemistry. Because if we detect these lines, and this is the same for the lines in the mid-infrared with photodissociation of water, this is going to validate our chemistry view of the interstellar chemistry. That means we're going to be sure that OH or CH+ are formed via these reactions. So that's very powerful if we want to understand the chemistry in this region. Unfortunately, even though we already have our data, because they've been observed in September and January, most of the results that we have are under embargo because this is the works of hundreds of scientists, so I cannot share the results with all of you. But I think most of them are going to be submitted or published very soon. So if you're interested in our works, stay tuned. Look at us on the internet for PDFs for all to have all our very beautiful results in these regions, and I'm sure they're going to be a lot more. Thank you for your attention. I hope I was not too quick and it was not too difficult for you. If you have any question, I would be very happy to answer to all of them.
Yeah, absolutely. Do not hesitate to ask your question in the chat room. So we have to wait a little bit because there is a bit of delay. Your presentation, by waiting, your presentation was amazing.
Thank you very much.
We have a little, can we see, there is a question, can we see things that you research in other galaxies?
If my research could be applied in other galaxies? Actually, yes. What I'm doing, so I'm doing it in the Milky Way. So the regions I'm studying are not in extragalactic, but what I'm doing, studying this kind of processes, could be observed in other galaxies. Yes, it's a bit different because I'm working at very small scale. So I have information on very small scales, but we could have spectrum that are averaged on a galaxy, and it is indeed could be applied to other objects. That's why we hope, and that's what we hope to make the community understand, that maybe these lines could be observed in very different objects, extragalactics also, yes.
Okay, thanks. Another question from Anaklo. James Webb could do it?
Could do what? Detect these lines?
Yeah, I think.
We really hope so. Maybe not in the PDR because, as I've shown you in my models, we really are the limit of detection for these lines. But in denser objects such as protoplanetary disks, so in the protoplanetary disk that we have in the field of view of the Ariane bar, we're pretty confident that these lines could be detected. And we really hope that we're going to be able to make a lot of results out of them. It's still good to understand that these lines are very faint. So even with this telescope that is very good and have a very high sensitivity, we are still looking at lines that are very close to the noise. So this will not automatically be easy to detect them in large various regions, but we are confident that we can see in some other regions with James Webb, yes.
Okay, very interesting. It seems that there is no more question. May we just wait a little bit? It seems no. Okay, so thank you, Madame, for your exciting presentation. If there is no more question, I would like to introduce Merlin Récuzon, Secretary of the Youth Commission, who will clarify the useful concept of Lagrange points. Merlin, the floor is yours.
Thank you, thank you. So I'm gonna sharing my screen. Okay, can you see it?
Yeah, totally.
Okay, perfect. So hello, I'm Merlin. I'm the secretary of this commission, and I'm gonna explore a bit further the concept of Lagrange point and what are they used in astronomy and astronavigation. I cannot. Okay, so there are the 5 Lagrange points. Lagrange points are generated when we have 2 mass, generally one heavier in the mass 1 in the middle, and another mass like maybe the Earth, while the mass 1 would be the Sun, in orbits. We have here 5 points, L1, L2, L5, L4, and L3. So at all of these points, we have a sort of stability. I mean, if we put some light object in L4 or L5, he will stay in place eternally and perfectly without any problem. In this place, you have the gravitational forces of the Sun and the planet, which are compensating the angular momentum. So, in fact, it makes you stay in the same position for a long time. For another part, we have 2 points extremely stable that are L4 and L5, but also some points that are a bit less stable, but still extremely stable, the L3, L1, and L2. The JWST has been placed in L2. Why? Because it has many interests. So first of all, it's a Lagrange point. So you do not need fuel, or you need a small quantity of fuel to stay in place. So the telescope does not have to take with him a huge reservoir of fuel, air goals, etc. It's just okay, it can stay with like a few corrections sometimes. From another point, we have the Earth between the Sun and the telescope. So, because he is observing in infrared and also in visible wavelength, it will not be perturbated by the sun's emission because the sun is extremely hot. So it produces an amazing amount of radiation, like light and I would say infrared. But thanks to the Earth, we will not see them and we will not be touched by them on the screen or the scope while observing at the Lagrange point 2. Another point linked to the sun is that you have no problem of cooling because the sun, every object in space, when they are exposed to the sun, they are extremely heating. So it could be extremely damaged, or more simply, just it could not observe correctly because the scopes need some really low temperatures. In this way, having the Earth between the sun and the scope, one more time, allows it to be less cooled and to stay at some, like I believe 7 Kelvin maybe, so extremely low temperatures without needing extremely important cooling system or anything else. And there is a last advantage of the Lagrange point L2. It's because we have the moon. The moon is not in front of it. The moon is like between the L2 and the Earth. So the Lagrange 2, when we have a telescope at this place, it will not be, it will not see in front of him like things like the sun, the Earth, the moon, or anything, light pollution, Earth's atmosphere. All of these are not perceived from this point, and so it allows a scope to work extremely well and have an unobstructed view to the deep sky and all the universe. That was all for me. I believe it was pretty clear. If you have any question, I beg you to ask. It will be a pleasure answering you. I'm waiting for.
Yeah, totally. Thanks, Merlin.
All right, please.
It seems that there is no question. Apparently, we have to wait a little bit.
Yeah.
Yeah, it seems there is no question.
Yeah,
so
anyway,
thank you,
if you
Merlin.
have some, oh, sorry, but anyway, if you have some, you can just ask in the chat and I will answer.
Yeah, the staff will be pleased to answer you. So thanks you, Merlin. Ladies and gentlemen, we'll now take a 5-minute break. When we return, we'll be joined by Dr. Elbaz from the French Atomic Energy Commission and Haikintana, the association behind the first automated observatory in Madagascar. Please take this opportunity to stretch your legs. The staff will be pleased to answer any of your questions in the chat room. So please do not hesitate. Keep in mind that the description contains the program of our Congress and other useful information. We'll resume this stream shortly. Thank you. Welcome back and welcome to all the new spectators. I hope you enjoy your break. We'll now continue with the rest of our conferences series, starting with Dr. Elbaz and his conference, JWST, the Promise of the Dawn of the Universe. Following this lecture, we'll welcome Haikintana, the Malagasy association behind the first automated observatory in Madagascar. So first of all, I have the great honor of welcoming Dr. Elbaz. You are the scientific director of the Astrophysics department at the French Atomic Energy Commission. You will be discussing the exciting promise of the JWST in studying the dawn of the universe, with the first images already released and scientific papers being published at an accelerated pace. The JWST is set to change our understanding of the history of the universe. What a program! We'll relay your question live to Dr. Elbaz, so please do not hesitate to ask them in the chat room. Sir, thanks you for coming. The floor is yours.
Thank you very much, Alexandre. So hi, everybody. So I will speak about the latest results that have been obtained with the James Webb Space Telescope about what we call the dawn of the universe. So what do we mean by the dawn of the universe? After the Big Bang, there was a time during which there was no star formation. The universe was very warm. 380,000 years after the Big Bang, the universe became transparent at the moment of the formation of atoms. And then came what we call the Dark Ages, a period during which you have no star formation at all, no galaxy, no planet. And then at some specific time, some hundreds of million years after the Big Bang, came the first star, or the first galaxy, or the first black hole. Who came first? When? How? What was the mass of the first object? Do they match what we understand from the physics that we have in our laboratory? Do they match what we understand in terms of cosmology, the role of what we call dark matter, possibly even dark energy? The age of the universe, is it consistent with what we observe? All those questions can be addressed by trying to address the question of when did the dawn of the universe happen? And for that, what we're looking for are the first generations of stars that we call the population 3 stars that were born in the first generation of galaxies that we call the primordial galaxies. A typical signature of those stars, which were born in a gas made out of mainly hydrogen and helium, is that they are probably very massive stars, up to typically 1,000 solar mass. And the most massive of those stars may have collapsed spontaneously into a seed of what will become later on a supermassive black hole, possibly at the center of a galaxy. So it's also the question of the birth of the first supermassive black holes that is behind this quest. So on December 25, the day of Christmas 2021, the JWST was launched. We have an image of the satellite obtained by the other satellite called Gaia, which is also at the point L2, distance of 1.5 million kilometers away from the Earth. You can see on this image the little dot close to a star, which is in projection and which disappears in the other green square. And that little dot here is the image of the JWST. So it's not a fake news. JWST is there and is observing the dawn of the universe. But it's not staying at an exact position where it has been put. It is turning within an orbit, which is very large, in fact, about 1 million kilometer diameter, and it takes 6 months to do each orbit, and it's connecting, transmitting information to the Earth with antennas that are in Australia, in Spain, in California, twice per day. The first images of the James Webb were amazing. And it was on the first page of all the newspapers, and everybody was looking at them, including the most famous astronomers of the planet, Joe Biden, Emmanuel Macron, and all the presidents were showing these beautiful images that were an example of a success of humanity. Of course, they are probably not the ones that will tell us the secrets of the dawn of the universe, but I want to say something about the acceleration of the results that came out after the first observations, and sometimes even an excess of excitation that led to some sort of excessive statements in the web. You have here a famous theoretical physicist, Michio Kaku, who does a lot of science popularization, which is appearing on a video entitled "Did the Big Bang Even Happen?" and where it is said that a group of galaxies at the dawn of the universe have been found, so famous primordial galaxies, by the James Webb. And they are so massive that to explain their formation, they will need to start their formation before, much before the dark ages, the cosmic microwave background epoch of the formation of atoms, even before the Big Bang. So that would mean that the Big Bang did not even happen. In 3 days, that video obtained 1 million views. And it was said it's the mother of all shocking discoveries. They even added that the movie, the series, The Big Bang Theory has to change their song, which is how whole universe was in a hot, dense state when nearly 14 billion years ago expansion started. It was on the first page of many newspapers, and not necessarily only any newspaper like the secondary newspapers, but even some main ones. And the claim was that probably we are finding something which is changing completely our picture, our understanding of the universe. So I suggest that we calm down a little bit and we try to understand what's going on. And I will try to give you some elements to understand what did James Webb actually really see, what is new, what is surprising. I will list a series of 6 surprises that are questioning our understanding, but not necessarily at the level that people have been questioning. And to start, let's wonder, why do we call this telescope James Webb, by the way? Who is James Webb? In fact, he's not a scientist. There is a very interesting you can listen to a discussion, very interesting discussion between the president in the US in 1962, John Kennedy, and James Webb, during which you realize that James Webb was the administrator of NASA who tried to convince the president that in order to go on the moon before the Russians, the United States needed to have the most intelligent people. And to get them, what James Webb tried to explain to Kennedy, they needed to not only tell them that they needed to go on the moon before the Russians, but they needed to go to do some science as well. So there is an interesting discussion where John Kennedy explains that he's not going to spend that much money for pure science. He really wants to go on the moon before. And in the end, what has happened is that James Webb was able to use a little fraction of the money for the conquest of the moon to do science with it. And the James Webb Space Telescope, in some sense, is a descendant of this policy where we try to where the conquest of the moon is followed by the expansion of not only humanity in space, but our knowledge in the universe. So we may wonder, after Hubble, 30 years more or less after Hubble, what remains to be done by the James Webb? What did Hubble discover? Hubble discovered that the galaxies were found very early. The most distant galaxy that was discovered by Hubble was observed at a redshift of 11, which is some 400 and something million years after the Big Bang. It revealed the shape of distant galaxies. It demonstrated that black holes were not only present in extreme quasars, but that galactic black holes were ubiquitous. In the end, it is more difficult to find a galaxy where you don't have a supermassive black hole in the center than a supermassive black hole, than finding a galaxy with a supermassive black hole. It refined the measure of the age and expansion rate of the universe, and it detected water vapor around giant exoplanets. So you may wonder what remained to be done by the James Webb. In fact, very early on, and it even started more than 30 years ago, we knew that there was a limit that was going to be reached by Hubble, because the light is shifted in the red, is redshifted, and the most distant galaxies will not be accessible to Hubble. Therefore, the dawn of the universe may be hidden to Hubble. And it started with some first concepts by a French engineer named Pierre Bailly, who worked at the Canada-France-Hawaii telescope, and then he worked at Hubble. And the head of NASA at the time, Riccardo Giacconi, asked Pierre Bailly, Peter Stockman, and Garth Illingworth, 3 astronomers, to think beyond Hubble 5 years or more before even Hubble was launched. And they started thinking of the concept of what was called the next generation space telescope. And you can see on this little cartoon that it looks already very much like the James Webb Space Telescope that has been launched. In practice, we have to compare the James Webb not to Hubble, but to Spitzer, which had only an 85 centimeter telescope in the infrared. And if you look at the images that we were expecting from the James Webb as compared to those of Spitzer, the one on the left here is what we were able to see with the Spitzer, and that's a simulation which is more or less comparable to what we have now with the James Webb, and you can see we can have a much better view on the shape of galaxies. It's the first time we had a deployable mirror in space, the first time we have a multi-object spectrograph in space, the first mass coronagraph in space, and 2 instruments built in Europe, and in particular one, the imager of the instrument MIRI, that was built with the CA as a main contractor for this instrument. Now, why do we observe in the infrared? There are 3 main reasons. Distant galaxies are redshifted. Dust absorbs the light of stars and remits it in the infrared. So if you want to see stellar birth, you have to look in the infrared. And third, to look at the shape and mass of galaxies, you need to look in the infrared, and I will tell you why. So, are the results there? Here is the image that was shown by Joe Biden on Monday, July 11th. The first thing you can see are stars, which are a few light years away, and then some galaxies that you can see in white that belong to a galaxy cluster, a family of hundreds of galaxies. We see them with a delay of 4.6 billion years, so it's not that far in the past. It looks far, but it's about the time of formation of the solar system. We see them when the solar system was formed. It's the moment when they emitted their light. 10 billion years in the past, we can see, thanks to the gravitational lensing of the mass there, the amplification and deformation of the images of the galaxies that are in the back, behind the cluster. And we can see the detailed shapes of those galaxies. Here down on the bottom right, you see the same galaxies magnified and seen twice, and you see some globular clusters in them. I will come back to this point because it's an interesting discovery. And finally, the Graal, which is the reason why James Webb was launched, are the little red dots that are the candidate galaxies that may correspond to the first galaxies formed at the moment of the dawn of the universe. Here, the first ones that were observed in this image come back to 700 million years after the Big Bang, 800, 1.2 billion years, 2.5 billion years after the Big Bang. So how does it compare to what we knew before James Webb was launched? Here is the galaxy that was detected by Hubble, which had the record GNZ11, and it corresponds to the Big Bang plus 415 million years. In fact, James Webb went back to this galaxy, did a spectrum, looked at the position of all the emission lines in the spectrum, and found that the distance of this galaxy was a bit less than expected. And in fact, we see it 436 million years after the Big Bang. Yet it is more distant than the first galaxies I showed you from James Webb. The first thing I want you to notice here, this is a spectrum of the galaxy that you can see here in 2D, and here you have the 1D spectrum. This is full of signatures of atoms, magnesium, helium, hydrogen, oxygen, which at a level what we have never seen before. Normally, a spectrum like that corresponds to the signature of atoms you can see in a very nearby galaxy. To see that close to the dawn of the universe is fantastic. And it's like a book that you open, which is written in a language that you've never seen, and now you need to decode the understanding of that. And we even see lines we didn't even expect, like auroral lines, which allow us to calibrate the amount of metals in those first galaxies. And that means that we will be able to have a much better understanding of the age of the stars that are in those galaxies, and therefore the moment of the formation of the galaxies. Now, have we succeeded to go further than that? Yes. The most distant galaxy ever observed to date in the universe, which is telling us that the dawn of the universe is at least at that time, is that guy, JWST 30, at a redshift of 13.2, which corresponds to 322 million years after the Big Bang. It's this little red dot here. And it is about 100 million years earlier than the galaxy I showed before, GN-11. And in fact, we have several which are more distant than that. Now, you may think that this is not so much. We only go 100 million years further. And indeed, that's not necessarily the most important aspect. And in fact, we've been looking for the signature of what we expect to be the first populations of stars, what I called before the population 3 stars. And that signature is expected to be a strong emission line at a wavelength of 1,640 angstroms, which is a line of the helium ion. And this line is absent from this galaxy. So what does it mean? It means that the stars that we see there are not the first stars of the universe. Therefore, they go further back in time. And when we estimate the age with an approximation of the age of those stars in that galaxy, we can deduce that the stars were formed about 770 million years before the moment when we observed the galaxy. So the dawn of the universe is at least 250 million years after the Big Bang. Okay, so we have found distant galaxies. We think that the dawn of the universe may be at least 250 million years after the Big Bang, maybe a bit earlier. No sign yet of population 3 stars. Now, 10 months after the first data release, I would like to emphasize 6 surprises. Surprise number 1. Distant galaxies do not look at all like we would expect them to be. They are extremely compact, so compact that it's very difficult to understand how it's possible. Now, let me tell you why I insist on that and how we know that. On the right-hand side, what you can see, those red dots are the most distant galaxies that I mentioned before to you, those red dots here, which look very tiny. And on the left-hand side, those are galaxies a bit less distant, a bit bigger. So they have a few hundred parsecs, which means a parsec is 3.3 light years. And here they are between 50 and 165. So it's about 200 light years of size. It is very, very small for a galaxy. In fact, it's not so far from the size of what we call a globular cluster, which are these associations of stars within the Milky Way that are free-floating in the Milky Way. Now, I show you a curve here with a galaxy of different shapes as a function of the age of the universe. What I'm trying to show you here is the following. So first, before looking at the curve, just listen to me. A galaxy is very far from us, one of those galaxies, and it's emitting light. Okay, the photons are escaping the galaxy. Now, before they arrive to us, what will happen to those photons? Because of the expansion of the universe, their wavelength will be expanded, they will become redder. That's one point. But there is a second point. Because of the expansion of the universe, it acts as a loop. It will magnify the size of the galaxies because the expansion magnifies the images. So it doesn't only extend the photon wavelength, it magnifies the images. That means that an object that is further away from me is supposed to be smaller, apparently smaller because it's further away. But in fact, because of the magnification of the image due to the expansion of the universe, it is nearly exactly counterbalanced by the expansion, and that is what this curve is showing you. It is showing you that when you look at an object further away from you, the curve rises. That means that you need a bigger size to cover the same physical size. That means the object is, if an object is further away, it will look smaller. But then you reach a maximum, and then it goes in the opposite direction because of this effect of loop of zoom of the universe. In practice, over most of the history of the universe, astronomers know that when you look at 1 arc second in an image, it is more or less 25,000 light years. So as a result, you can nearly use a ruler on your screen to measure the physical size of galaxies. So why do I say that? I say that to tell you that the little red points you see in the close to the dawn of the universe look little because they are intrinsically little, they are tiny. Now the question is, how could you produce such tiny objects so early in the history of the universe? That's the first surprise. Second surprise, distant galaxies are much more numerous, bright, maybe even massive than expected. In fact, as a colleague said, we have seen in a few days more than what we expected to see in a year. What you see in those figures are illustrations of this very fact. Here at a redshift of 9, so that means further away in the universe, like close to the most distant galaxies. The points here are the number of galaxies that we see in a given box of the universe. So if you are high, vertically high, that means you have a lot of objects, and if you are low, you have not that many. And the blue curve is what was expected before. And you see that here, and here we are among the most luminous in the UV, in the ultraviolet, because its magnitudes, the most luminous are on the left, because a low value of the magnitude means a brighter object. And you have an excess of 10 to 100 times more objects than expected. If you go further away, this time at a redshift of 12, where you would expect between 0.1 and 1 galaxies, you see 4. So we have much more objects than before, and that's the reason why people are starting to think that something is wrong in our expectations. But how wrong are we? And then came out a paper in Nature by Ivo Labbé et al., who claimed that when you measure the actual, not UV luminosity, the power radiated in the ultraviolet, but the mass of the galaxies, the problem is even sharper. The curves that you see here are what you were expecting before, and here the zones are what you observe in terms of number of stars per unit volume, or mass of stars per unit volume of the universe. So that's when people have been starting to think that you need more time to form those galaxies. One paper came out that said that to form those galaxies, here you have the stellar mass of the galaxies, and just 2 of those galaxies here are so massive, so early on in the universe, that they start to enter into a zone. So the amount of mass per unit volume in the box is so high that you would need to use all the mass made of atoms in a given region and convert it into stars to make those galaxies. You nearly need to convert even dark matter into stars to make those galaxies. So it's becoming crazy. In fact, we are wondering whether the mass of those galaxies are correct. But here, that's what this paper was claiming. And another paper came out saying that you can reject the expected model for what we call the dark energy, so the cause of the accelerated expansion of the universe, at the 90% level. I won't go into the details of those papers, but those results are the reason why you had what I showed you before in the first place, where newspapers started to claim, and some scientists, that maybe the Big Bang didn't happen, but not serious scientists, just, people who really wanted to, let's say, go a bit quick in the job. Now, the scientific context in which you have to consider those results is important because it's complex. So let me try to summarize a little bit of the complexity. Sorry, I left some French here. The expansion of the universe prevents the collapse of matter, and so gravity has to fight against expansion. And we believe that it's dark matter that helps the formation of the first galaxies. So the first fight is between expansion and gravity. There is a competition. Then when matter falls, there is a competition between the agitation of matter that collapses and gravity. So there is what we call a Jeans criterion that was written in 1902, where you have an equilibrium between agitation and gravity, and you form a structure. But then the structure starts to rotate, and that prevents the collapse. So another thing is in competition with gravity. So first, the expansion of the universe. Second, the agitation, the thermal agitation of matter. Third, the rotation of matter. Fourth, the turbulence of matter that can be produced by the rotation, but also by the explosions of supernovae or by the presence of quasars. And finally, inside the star, it's the competition between nuclear fusion and gravity. So in the end, you have a complex process to produce stars. And when you see some light coming out from a galaxy, it's very difficult to know what is the mass of the galaxy, because you need to know what are the number of low mass stars, high mass stars. And when you want to see if the galaxy was formed too fast compared to what you expected, you realize by this little schema that I show you here that what you expect is highly uncertain, because you need to understand all those 5 processes well to be able to say precisely what you should expect. So in fact, we don't control that so well. So the fact that our expectations are not correct is not so surprising. But there is another reason. What we have realized by looking at the galaxies that were considered to be too massive to be formed after the Big Bang is that in many of those galaxies, the light that we are collecting is not coming even from stars, but it's probably coming from supermassive black holes heating the matter in the surrounding of the black hole. And that is very surprising, because we knew, and as I said, Hubble showed that there are supermassive black holes in the center of all galaxies. But what we didn't know was that they were formed very massively, very early in the universe, much more than expected. I go back to this galaxy that I showed you before, which is the spectrum of the first galaxy, or the most distant galaxy that was detected by Hubble. And in fact, zooming in on the spectrum, what we found are signatures of ions that are typical of another process than stars to heat the gas. And the process is the accretion of matter, the matter that falls onto a black hole, that is heated at very high temperatures and induces some extreme excitations of the atoms that you can see here in red in the square here where I zoomed. And that's the signature of what we call an AGN, which is an active galactic nucleus. That means, in other words, a supermassive black hole. So that galaxy, which was found to be the most distant galaxy with Hubble, turns out to be a small quasar. And if you try to estimate the mass of galaxies where a good fraction of the light is powered by a black hole, you will be wrong, because you will think that the light comes from that much mass of stars. In fact, it's just one single black hole. So the consequence of that is summarized in this a little bit complex diagram, but I will summarize the most important idea here, is that in the past, we thought that the seeds of supermassive black holes were the first 1,000 solar mass stars, population 3 stars, that collapsed into a black hole and then grew in mass. Now, what we realize is that the universe has black holes which have been formed so early in the history of the universe that that process doesn't have the time to happen. So now people are thinking, after the results of the James Webb, that probably the first thing that was formed in the universe were stars even more massive, or concentrations of mass so massive that they directly formed a black hole, which can be as high as 1 million times the mass of the sun. So you formed spontaneously by a direct collapse a black hole of 1 million solar mass. That is what is now probably favored by the latest results of the James Webb, and that came as a surprise. Surprise number 4, spiral galaxies like the Milky Way were already in place a few 100 million years after the Big Bang. That is a very important surprise, because a spiral galaxy is a very fragile galaxy. You can easily destroy the disk of a galaxy because it's a thin disk which each time you have a merger with another galaxy can be either destroyed or become thicker and not remain thin. How did galaxies survive for a long time if they were formed very early on in the history of the universe? Now, to do that, how did the James Webb succeed in seeing the shape that Hubble couldn't see before? I tried to summarize that with this image. On the left, you have one massive star of, let's say, 10 times the mass of the Sun. On the right, you have the same massive star, but surrounded by thousands of low-mass stars. Now, the amount of light radiated by one star of 10 solar mass is 4,000 times the luminosity of the Sun. It's equivalent to 4,000 suns and tens of thousands of stars less massive than the Sun. So that means that when you see some light, it can either come from one massive star or from thousands of low-mass stars. But to see the low-mass stars, because they radiate either in the visible or in the infrared, and because their light is redshifted in the infrared, because galaxies are distant in the universe, you need to look in the infrared. So I summarize that by saying that Hubble was not able to distinguish a squirrel from an elephant because it couldn't know the mass and the shape of a galaxy if it was distant, because it was only able to see the most massive stars that radiate only in the ultraviolet. And it couldn't see which was redshifted to the visible that Hubble could see. Now, with the James Webb, we can separate a squirrel from an elephant. And here is an example. On the left, you have a squirrel. What Hubble saw of a galaxy, which looked like a bit irregular object with some clumps. And on the right, you have an elephant, which is what you actually see from the James Webb by having a bigger mirror with the capability to see fainter, low surface brightness emission, to see in infrared. And then you see that what looked like an irregular object is in fact a spiral galaxy. And the James Webb was able to see spiral galaxies up to 600 million years after the Big Bang. Of course, the quality of the image is degraded when you go very far away because it's difficult to see what we call low surface brightness emission, but you clearly see some nice spiral galaxies, very well formed, very far in the past. And that is a big surprise. How did those galaxies form? How did they survive? What's funny is that Hubble had invented what we call the Hubble fork, and galaxies were classified as ellipticals, spirals, or spirals with a bar. And it looks like a fork, that's why it's called the Hubble fork. But then the Hubble telescope showed that in the distant universe, in the past, the shape of galaxies were very irregular. They didn't look at all as galaxies you could classify with the Hubble fork. So the Hubble Space Telescope killed or broke the Hubble fork. But then James Webb is resurrecting the Hubble fork by showing that, yes, you do have some nicely well-formed spiral galaxies even early on in the history of the universe. And that's very important because spiral galaxies are, as I said before, the place where rotation is in competition with gravitation, and that produces what we call some sort of self-regulation of star formation. That means there is a smooth star formation activity over the time in the galaxies. And the image you see on the right-hand side here is the image of a spiral galaxy seen with the MIRIM camera, at colors, at wavelength, where the source of light are complex molecules. That means that what we are witnessing here is the formation within the arms of the galaxy of complexity in the universe, because those molecules have CC and CH bonds that rotate or vibrate and radiate a specific wavelength that you can collect with this camera. So that means that the light that you see here are telling you where the complex molecules are presently being formed in the spiral waves of the galaxy. And you can see here bubbles that are corresponding to the explosions of supernovae that are inducing the turbulence that I was speaking to you about before, which is the other competing process against gravity. But surrounding the bubble, where you have a shock wave, you have compression of the gas that induces even more complexity, even more star formation. Each time a star dies, it generates new stars. So you have here the full cycle of life of stars and the self-regulation of galaxies, which are producing complexity. And you can see maybe the first stages of the recipe of life in some sense, because those complex molecules may be at the origin of what will become life in the future. Surprise number 5, galaxies started to die, to become passive, to stop forming stars much earlier than expected. And we wonder, how did that happen? So you have here the spectrum of one of those very compact distant galaxies. And the zoom here is showing you now some absorption lines. So you see that atoms are absorbing the light of the star in the atmosphere of the star, oxygen, calcium, hydrogen. And to be that strong, those absorption lines, they require that there is no, because that's the sum of the light radiated by all the stars present in this galaxy. So if there were massive stars that were newly formed, they would produce a continuum emission because they are so warm, so hot, that they completely ionize the atoms in their surroundings, and you don't have these absorption lines in those stars. So if those newly formed stars were there, they would completely erase those absorption lines. The fact that you see them so clearly is the proof that no star formation has taken place in that galaxy since several 100 million years, even though the galaxy is only seen 1.2 billion years after the Big Bang. In other words, this galaxy must have died, become unable to form stars very early after the Big Bang. And the question is, why? What is the reason that caused a galaxy to stop forming stars so early in the universe? That's another surprise. And I will come back to all those surprises, and I will first tell you the 6th one, because there is possibly a single explanation for all of them. Surprise number 6. Globular clusters are very common and old. Here you have a galaxy called, that has been called by authors, the Sparkler galaxy. It is not so far away, it's 4.6 billion years after the Big Bang. Yet what you can see is that it is full of dots that are globular clusters that we could study in detail, and this team has been able to measure the ages of those globular clusters and found that they were 4 billion years old. So to be 4 billion years old in a galaxy that you see 4.6 billion years after the Big Bang means that those clusters were formed probably around cosmic dawn. So now there is a new question. We wondered if the first things that formed in the universe were stars, galaxies, or black holes. In fact, it may be a fourth object, globular clusters, because we see those old globular clusters, and many galaxies, we see many of them. So that's a new mystery, a new surprise from James Webb. So if I summarize all those surprises, we see that distant galaxies are present, they are numerous, but they are also very compact. It's extremely difficult to understand how the universe was able to make galaxies so compact. Supermassive black holes were formed earlier than expected because they are more numerous, more massive than expected. In many galaxies, we see the signature of those supermassive black holes of several million, sometimes 100 million solar masses, only a few 100 million years after the Big Bang. Not all galaxies were spiral, of course, in the universe, but we do see many spiral galaxies already well-formed, already in place, only a few 100 million years after the Big Bang. That's also a surprise. Galaxies started to die, become passive earlier than expected. What's the cause of that? And globular clusters were very common. Now, there may be a missing link between all those surprises, which is what I show here, where you have cold filamentary infall of matter onto a galaxy. This is an artistic view of something that is invisible even to the James Webb, this diffuse matter that we think is infalling onto galaxies. Now, it could be responsible for many things. First, there is a recent paper claiming that if you consider those converging filaments early on in the history of the universe, they could be responsible for the ultra-compact sizes of galaxies. Also, they may happen faster than the time it takes to generate the competing phenomenon against gravity. You remember I spoke about turbulence, I spoke about supernova explosions that are preventing matter to collapse and form stars. But that takes time for a star to explode. But there is a paper by Haikintana et al. Recent also that claims that the filaments may be able to form stars even before the reaction against gravity happens, making them more efficient to produce ultraviolet light. So first point, making them compact. Second point, making them more efficient in forming stars. Third point, another study claimed that it may be even possible that converging filaments helped forming seeds of very massive supermassive black holes early on in the history of the universe. Fourth, the filaments, they don't arrive directly in the direction of the center, they are slightly offset. As a result, they induce some rotation of the galaxy, and simulations have shown that you can inject what we call angular momentum on galaxies by those filaments, and therefore explain the early formation of spiral galaxies. And why do they survive? Because they are continuously fed by those filaments. In fact, we can even revert the situation and say that the fourth surprise may be the strongest evidence in favor of infalling filaments like that, because otherwise we would not understand the formation and the survival of spiral galaxies over the whole history of the universe. Fifth, galaxies started to die and become passive earlier than expected. In fact, what we realized is that the matter to form stars within a galaxy is only enough to form stars for a few 100 million years. Galaxies form stars thanks to the matter that is infalling onto them. But if you cut the filaments, for example, if you have some shocks or if you have some surrounding galaxies taking the matter, like in the proto-galaxy cluster, then the galaxy will die very early on. So you can explain number 5. Number 6, globular clusters are very common and all. You may induce with these filaments some what we call dynamical instabilities that produce some clumps. This is here just again this image where you see with an artificial intelligence image that I generated by combining a wave and the image of this galaxy to show that in the spiral wave of the galaxy are generated clouds in which stars are formed. And this process may be the reason why we have been finding that galaxies seem to form their stars with a very universal manner over the whole history of the universe, possibly due to this regulation of star formation. And at the time we are talking together, the solar system is moving at 800,000 kilometers per second around the center of our galaxy, participating to the generation of density waves that produce this foam in the cosmic sea of the disk of the Milky Way, in which new stars will form. So in some sense, we participate also to the generation of new stars, and we participate to the cycle of life of the universe. So this is what I wanted to say to you today. Thank you.
Thank you, Mr. Is there a question? I will relay they to you. Thank you for your presentation. That was really interesting. So we have to wait a little bit because there is a little bit of a delay.
Oh no, you actually appears like speaking. So I'm looking at what you said when the conference will be over on the live.
Yeah, no, there is no question, I think. I see no question.
Oh,
so
okay.
Thank you, sir.
Please it's just ended on the live, so just maybe wait a few seconds more.
No, there is no question. So thank you, Mr. That was really amazing. And Merlin, the floor is yours.
So, well, first of all, excuse me, I'm gonna maybe put my camera on. Okay, that's better. So, first of all, I would like to obviously thank Dr. Elbaz for this amazing lecture. It was a real pleasure to hear it, and thank you, really thank you. I would also like to express my gratitude to our speakers who have provided us with an insightful view of the new era opened by the JWST. However, it is now time to indulge in the pleasure of stargazing. Therefore, I would like to introduce you to the Beasley Observatory, managed by Haikintana. Haikintana is a Malagasy association that aims to promote the role of science and scientific education in Africa. In partnership with the French Astronomical Society and the UNESCO, they have established the very first observatory in Madagascar, which is fully automated and equipped with powerful instruments to discover new skies, all benefiting from exceptional observation conditions. You will be the first to benefit from it, so I hope and I am sure that everything will go fine and that all of us will be amazed. One more time, if you have any questions, don't be afraid to ask. We will have a short break in a few minutes. So I'm fully dedicated to answer interrogations of yours. Moreover, this will be a really interactive part, so don't hesitate. So now I would like to introduce you to Haikintana, Mializo, Ando, both of you are welcome.
Hello.
Hello. Please, could you talk us a bit about your association and how it has been created and what you are doing in Africa?
Okay. Okay. So let me just switch my.
Oh, no problem. Take your time. Take your time.
I think Mializo has a presentation, so if you want to share it, yeah, go ahead.
Yeah,
okay.
Perfect.
Okay, so hello everybody. So my name is Melissa Razanakutu. I'm the founder and the co-president of Haikintana Association. So today I'm just gonna talk a bit about what we are doing in Madagascar and in Africa. So our activities are mainly based in Madagascar, as you can see here in this image. It is actually a picture taken from the ISS that shows Madagascar. For those who don't know, where is this country? So we are just near Africa, in southwest of Africa. So let's start with the beginning. In 2015, we created the Haikintana Facebook page, where we started to promote astronomy in Madagascar. So it started on social media. It's good to mention because Facebook is one of the main communication channel in Madagascar. So it was kind of easier for us to reach our target through Facebook. And then after, and the year after, we started the community Haikintana that was composed with students in different fields, different backgrounds, but especially in physics, astrophysics from the country. And since 2018, we are officially an association. So it's good to mention that the community is mainly composed with young Malagasy astronomy enthusiasts that are just here to share knowledges, opportunities, and different and exchange anything about astronomy. And together we have the vision to, as I told before, to promote astronomy in Madagascar in order to inspire the future generation to scientific fields. We also aim to be a platform of exchange between professionals and amateurs in astronomy in Madagascar and all around the world. So we have different goals that we are wanted to reach. So first, we wanted to create a new center of interest for the young Malagasy people. And of course, we are supporting a lot educational and scientific projects. So we help all the passionate in astronomy to create and to manage their projects and to make them actually real in order to reach any goals on this field. And of course, we wanted to use astronomy as a lever for development of a country. And one of activities or one of the projects that actually we have worked on and are still working on is the BESELI project that we are talking about it after. Briefly, here are our divisions. So in order to actually manage all the projects that we are working on, we have educational department, outreach department, partnership department, and of course, the one that we have just created, all about the observation and instrumentation that is there to train the members in the use of observation instruments such as the BESELI telescope and just use telescope that we are using like every day. So for the educational divisions, we aim to support the Malagasy educational system by visiting schools or working with association or other institutions in local or internationals. The outreach divisions we are here, it's mainly promoting science for general public. We are organizing a lot of exhibitions, conferences, and of course stargazing sessions. And partnership, which helped us actually build this relationship with French Astronomical Society. So we really want to use these sciences to add more value to the country. So here are some pictures of some of our highlighted events and projects that we have been working on from 2015 until now. As I told in the beginning, in the previous slide, also, is that we are participating in different science fairs, conferences, and also organizing our own stargazing session or other projects. So here, for example, we can see here the participation of Madagascar during the 17th annual conference that was held in Algeria, if I am precise. And then after, here are some projects that we have been proposed in Madagascar. Since 2017, we are organizing Asteroid Day, which is a global exhibition to raise awareness of the risks and impacts that an asteroid falling can make on our planet. And in 2019, we have also participated to the NAME-IXO project of International Astronomical Union, where we could name a planet, actually an exoplanet and its star. So we actually have Malagasy names of a star and an exoplanet. Here are some pictures from our stargazing session we had I think 2 years ago, and also we are organizing On the Moon Again, which is a project of French Astronomical Society as well. And as I said before, here's just a picture of one of the conferences we held at the school in the capital of Madagascar. So mainly we really like visiting local schools because we believe that inspiring and talking about sciences from the beginning, so from schools, and can make difference and can actually add something to the education. And of course, we also are working a lot with French Astronomical Society, actually. And so we organized the first edition of Universe, which is a challenge proposed by the French Astronomical Society, and on the Moon Again last year. And of course, we actually worked and still working on the astronomical observatory of Bécile that is based in Majunga, and is actually houses at the École du Monde Madagascar. So it's a project that it's in partnership with French Astronomical Society, the École du Monde Madagascar, which is actually an association that has a campus in the Bécile Majunga. So Majunga is in the northwest part of Madagascar, and where they have different schools. So they wanted to also add astronomy in their classes, in their courses. So together with the same goals, we created this astronomical observatory. That we will know more after, and that we will use after for the observation of skies of Madagascar. So that was my little presentation for today. So thank you for your listening.
Thanks, Mialiso, for your presentation. Ladies and gentlemen, we'll now take a 5-minute break. When we return, we'll be on an observation in live with your association, so that will be a pleasure. So please take this opportunity to stretch your legs. The staff will be pleased to answer you in the chat room. So please do not hesitate. Keep in mind that the description contains the program of our Congress and other useful information. We will resume this stream shortly. Thank you.
So welcome back, and we are gonna start the last part of our of this congress with a live observation from Besley in Madagascar. Let me introduce you to Ando, the person that will be in charge of our observation and manipulate the scope for us tonight. Hi.
Hi, Merlin. Merlin. So my name is Ando. I'm from Madagascar, and currently I'm the director of the Besley Astronomical Observatory that my colleague Miazu said before. So today we will observe the southern sky from Majanga, from Madagascar, and we will know at the observatory, we have the camera into the observatory, so you can see the telescope. It is a 14-inch telescope, which is mounted on EQ8 mount, and we have a monochromatic camera, a big camera, and it will help us to shot the sky, to do astrophotography, and also to do science. So this is the specificity of this telescope. So we have also a roof that slides automatically. So for this night, we will observe some object of the southern sky, as I say. So firstly, we will observe the galaxy. This galaxy is specific of southern sky, so you will not see this galaxy from the north. So this galaxy is located in the constellation of Centauri. We call it Centaurus A. So you can see the software that we use on the observatory is the Prism V11.
Excuse me, but maybe some people are. Could you explain why we can see some objects in maybe the North sky, but not in the south, and why in the north we cannot see the objects that you are gonna show to us?
Okay, because we are the inclination of the Earth, so some parts of the sky are not visible in the north, and some parts are not visible from the south part of the hemisphere of the Earth. So we have the Earth, it's a sphere, and it's inclined of I don't remember, 23 degrees. So Madagascar are located in the southern sky, so we can see some part, a great part of the southern sky. And you are located in France, in example, or in Sweden, so you cannot see the part of the sky that we can see in the southern sky, in the southern hemisphere of the Earth. Maybe it's answer the question.
Yeah, thank you very much.
So we'll search the object. It is Centaurus A. So now we can see the object because I typed the French name. So we have to type now the name from the catalog. So it is NGC 5128. So now we will point the telescope to the object. Yeah, forget to do it. So now we can see that the telescope is moving, but not in the direction that I want.
I don't know if it's possible, but okay, thank you. That's what I was about to ask.
Yeah. So now you can see the telescope moving. Turn off the night vision. So in the first time, we'll take something like 10 or 5 seconds of exposition to see if we are in the area of the object. Then if it is okay, we'll take it for maybe 1 minute. Yeah. So the center is.
So can you precise what is Centaurus A as an object, an astrophysical object?
Yeah, so Centaurus A is a galaxy. It's a galaxy in the constellation of Centaurus. So we think that it's a giant elliptical galaxy which have an active nuclei. So in the center of Centaurus A, we have a massive black hole. So Centaurus A is there. We'll now calibrate the picture that it will help you to see it clearly. So there, I don't know why the picture is like this.
We have to precise that the moon is 90% this evening, so it can be a trouble. But I think also that just one picture can be not enough, and we can we can use this technique of live stacking also. Do you have this? Can you use this technique with your setup?
Yeah, we use the stacking technique, but for this live, I will just took one by one pictures. Yeah, because it will take a lot of time if you do the stacking. So this is Centaurus A. So I have Centaurus A in my area. So now I will put 1 minute of exposure time, because when you have a long time of exposition, we'll collect more data. So now we have to wait 60 seconds. So we can discuss about something if you want.
Maybe you could explain us a bit how with the telescope working, like what can he allow us to observe? What is his capacity?
His capacity. So as I said before, it is a 14-inch telescope. So we are a small telescope. It's not a great, it's not a big telescope like James Webb, but with this telescope, we can observe deep sky objects. And also last year we observed we followed the DART mission from Madagascar, so we can follow also comets and asteroids. So that's that we can do with telescope now. Now we have more with the picture. Okay. So we have Centaurus A now in our frame. So you can see that currently in basically we have some winds. So we have some vibration on the telescope. So you see that some stars are moving, but you can clearly see the galaxy on in the center of the picture. We can see the galaxy there, and there the center of the galaxy, Centaurus A.
The important thing that we can remark there is those little squeezed stars can be corrected by perhaps more exposure, more frames, but less time of exposure, or a guiding system like auto-guiding.
Yeah, we can do that. We can do that. So our system are currently consider tracking with a special configuration, because we are done a calculation of the error of guiding telescope. So now we can do a single exposition of 2 minutes with our telescope without guiding, without using the guiding mode. But now this picture, I know that the condition in basically we have some vibration in the place. So this is Centaurus A. So we will now observe another object, which is also in the constellation of Centaurus. It is the Tweezers galaxy. So this another one, you can see this from the North Hemisphere. So Tweezers galaxy is a spiral galaxy, barred spiral galaxy like the Milky Way. But we will see that it is shown by profile. You can see that it is on the Centaurus galaxy, Centaurus constellation. So the telescope moves but a little bit. Right. So this is the Tweezers galaxy. The Tweezers galaxy is there. So we will take more time. So as I said, it's a bird spiral galaxy, the constellation of Centaurus. And if we can go out of the observe our Milky Way from the profile, we can see that our Milky Way will look like the Tweezers galaxy. So this is the galaxy. You can see the arms of the galaxy. So this is the tweezers galaxy, NGC 49445. And this is in the region of Centaurus, in the constellation of Centaurus.
Okay, excuse me. So we have a little question. What is the dark line? Can it be corrected? And why there is a white line on stars?
This one, because it's a very bright stars. So we have this white line, and I think you talk about this dark line. The question.
Yeah, I think he's talking about this one.
It's due to the captor of our camera, because it is the camera from T60 from the Pic du Midi, I think so. It's a default from the camera, So we correct it with the post-production, with the treatment of the picture. So we have to use another software to correct it.
In fact, also, I think that the drizzle method can correct this sort of problems, isn't it?
Yeah, I think. But when I took picture, I just crop it from the. It's more easy for me to crop the section when I do observation, so it's not really a problem for me. But sometimes when you took a more greater object, we can't see the problem. But for the smaller object like this, you can just crop it.
Yeah, totally. In fact, the drizzle method is to just move a little bit the image up and down on the side, so the error on the captor is not on the same place. So with the treatment and the stacking, we can just eliminate this sort of error.
Yeah, exactly. So these are two galaxies of the Centaurus constellation. So now we will observe one of the most beautiful things of the southern sky. It is a globular cluster. It is the Centaurus. It is Omega Centauri. So you can see there is the moon.
The thing is, because you have C14, the moon is too bright, even at 90%, is too bright to be able to observe it right now.
Yeah. And after that, our camera can't go for a very smaller time exposition. We can go in 0.001, we just can go in 0.5. So the moon is very brighter, so we can observe the moon at this condition.
There is a question.
Another question from Anaklu. Oh, sorry, Alexander, maybe you want to transmit it.
Yeah, go ahead, Marion.
Okay, thank you. So actually, we have a black and white picture, can we have a color picture, or why don't we use color picture in astronomy, or how to do it? In fact, why are we using black and white?
We have not a color picture because our camera is a monochromatic camera, so it's took a black and white picture. We have filter, but we don't use it now because our filter wheel doesn't work. So that's why we have always a black and white picture. Maybe maybe I don't know, in the future we'll have a new camera that can take a picture, a color picture, but currently we have just black and white picture.
But maybe for, I believe, some of the planetary observation, we use sometimes a color camera, right?
Yeah, right.
Okay. It's like, in fact, it's not the same use for the same objects.
Yeah. So now you can see that our object is not in the center of our window. So we have to recenter the telescope to the object. So we have just one function on our software, which is recenter the telescope on the object. So now when we took this picture, we'll see that our object, Omega Centauri, will be in the center of our window. So you can see it is in the center of a window. So I will take like the previous objects. Okay. So the Centauri, Omega Centauri is the largest star cluster of our Milky Way. So you can see it from the southern hemisphere. So that's why we love the southern sky.
Another question. Also, we heard today that the objects emit light for a certain wavelength. Do you have tool to extract this light? Like, I believe, spectroscopy?
No, we don't. Currently, we don't extract this light. So I will save it. So this is Omega Centauri of the Centaurus constellation. So when you observe this object with your naked eyes, we'll just see just a small point on the sky. But when you use a telescope, a large telescope, we can see that there is not only one object. It is not one star. It is a lot of stars in this region. So this is Omega Centauri. So now we will move in another object. Yeah.
Do you have an estimation of how many stars are there?
No, I don't have an estimation, but I think it's more than 100 stars. I think it's more than 100 stars.
Okay, thanks.
Yeah. So now we will move now in another constellation. I think you know this constellation. In the northern sky, you have the galaxy which has the same name of this galaxy. It is the Pinwheel Galaxy. Pinwheel Galaxy. But this is the Pinwheel Galaxy of the southern sky. It is a Messier object. It is the M83.
Just for curiosity, can you observe any type of objects with this scope? Like maybe, sorry, can you do it like maybe like planet, moon, or only deep sky, or what can you do with it?
So with this camera, with this telescope and camera, we can observe deep sky object like galaxy, like nebula, like planetary nebula, and but we cannot really observe planets because as I said before, we can go under 0.5 second for the exposure time. So sometimes when your planets have is a very brightest planet, so we can just see a white dot. So this is the difficulty with our camera. So we just observe deep sky object, and we observe also asteroids and comets.
Okay, thanks. Another question. If you say you don't have the key to do some spectroscopy, but can you? It is in your project. Is it in your project to do some spectroscopy?
Yeah, in the future, it's in our project to do that. But currently, we work with that we have. But it is in our project. So you can see this is the Southern Pinwheel Galaxy. It is a spiral galaxy, and it is in 15 million light years from the Earth. So I will take 60 seconds. So if we have not the moon this night, will see a more beautiful picture. Because we are in this region that the light of the moon touch the area of the galaxy.
Is there any question? Because do you have some new object after that?
Yeah, we have a last object after that.
Okay. Ladies and gentlemen, do not hesitate to ask some question on those objects.
So it's really difficult to have a clear. Okay, let's know. So there is the southern pinwheel galaxy. So you can see the center of the galaxy, the arms of the galaxy. So when we are doing observations, sometimes we took 2 or 3 minutes of a picture of the object. Then we use stacking, and we took more than 10, 20, or 30 pictures with 2 minutes each picture. So this is pinwheel galaxy. So southern pinwheel galaxy, sorry. So we will now observe the latest galaxy for this night, and the latest object. It is, maybe you know it, it is the Sombrero galaxy. Don't know if you can see the Sombrero galaxy in your location.
Someone asked if you plan to observe a nebula, but maybe visibly not, but maybe could we add a nebula to the observation?
Yeah. So
thank you.
You ask it, so we'll observe a nebula. It is the Carina Nebula. So now I have to type the coordinate of the location of the nebula. So we can do some stuff with the software. Sometimes if you are more familiar with declination and rate extension, you can directly enter it on the software. So you can see the camera, this big camera. So sometimes I'm lost with the software. 5, 8, 8. Yeah. So sometimes when you think that you are lost, we have to recognize the area with an astrometric resolution.
To help you in this way, you can use perhaps astrometry, no?
Yeah. Okay. Okay, we have the nebula, but I think that when I took the picture, the telescope is still moving. Yeah. So this is a complex area of bright and dark nebulosity. It is near the star Eta Carinae. It is a variable star. So all of these things that you can see, it is the region of the Carinae nebula.
So the interesting thing about a nebula is that in this sort of nebula, stars are there is stars that are burning. So it's a link with the second conferences that we have with Marion Zannese. It's in this source of nebula that stars are
forming.
Okay, so thank you. It starts to be a bit late, I believe, for the viewers. The live is on since for 4 hours. So I believe it's maybe the time to an end. Do we have anything to add, Ando?
So I want just to thank you for this event, for inviting us to take part to this event. It is a great opportunity to show to you the southern sky, the galaxy from the southern hemisphere, and the observatory of Bessel. So thank you.
Yeah, thank you, and thank you for taking place in this Congress with us. Alexander, may I let you end this Congress, please?
Thank you, Ando, for your participation. Dear attendees, as we come to the end of this exciting Congress, I would like to express our gratitude to our partners, National Center for Space Studies, French Atomic Energy Commission, Astronomisk Ungdom, IPSA VEGA, and Haikintana. Their support has been instrumental in bringing together leading experts from around the world to discuss the new space revolution that is the James Webb Space Telescope. Thanks then to the staff for the brilliant work that makes this Congress a reality.
And by the way, I would like to thank you, Alexander, for all the work that you provided, because I have to tell that you are the initiator of this project and you did hard work managing everyone and everything in order for this to be set up. So I would like to thank you very much. It has been a pleasure to work with you on it, and I hope we will do it again one day. Really, thank you.
Thank you. It was a really pleasure for me to direct this project. Then thanks to all the speakers and the Office of the French Astronomical Society for their trust. Finally, I would also like to extend a heartfelt thank you to all of you, the attendees, for your active participation and engagement throughout this Congress. Your thoughtful question and insightful contribution has made this Congress a truly collaborative and enriching experience. Thank you, everyone, and see you next year for the second edition of the International Congress of the Astronomical Youth. À l'année prochaine.